We built the most powerful time machine ever made, pointed it at the dawn of creation, and it sent back galaxies that look impossibly old. Not scattered sparks after a beginning, but massive, mature cities of stars already in place. So what's broken? Our measurements, our models, or the story of the universe itself? And is Webb hinting the Big Bang wasn't the absolute beginning? In the darkest frames of Webb's deep fields, the universe stops behaving like a clean origin story, and starts behaving like a crime scene. Every faint red fleck becomes evidence, and every assumption becomes a suspect. What we are really seeing is not a simple picture, but a chain of translations, from photon to filter, from colour to distance, from distance to time. Those translations are powerful, and they are fragile. A single calibration choice can tilt a spectrum, and a single template can turn dust into age. Emission lines can masquerade as a break, lensing can quietly amplify a source, and a hidden black hole can borrow starlight's disguise. Yet the tension does not vanish just because the pipeline is complicated, because the standard model is complicated too. It is an interlocking account of expansion, dark matter scaffolding, cooling gas, and feedback that should throttle how quickly galaxies ignite. So the question becomes sharper and more unsettling. Are we misreading the clock, or are we discovering that the clock itself is incomplete? If redshift is our measure of time, then the map from redshift to age depends on the universe's expansion history. That history is not guessed. It is fitted to a ledger of evidence, from supernovae to clustering to the cosmic microwave background. Change one parameter, and the early timeline stretches or tightens, subtly at first, then decisively. But the photons do not care what we prefer, and they do not negotiate with tradition. They arrive with their wavelengths stretched, their energies thinned, and their message encoded in probabilities rather than certainties. In this documentary, we'll follow that message all the way down, through the engineering that keeps Webb cold and steady at L2, through the statistical machinery that assigns redshifts, and through the simulations that try to grow galaxies fast enough. We will weigh the most conservative escape routes first, and then push toward the edges where cosmology becomes philosophy. Somewhere along that path, a familiar beginning may emerge strengthened, or it may deepen into something stranger than a single moment called the start. The stakes are not merely about a few anomalous galaxies. The stakes are whether our measurements are missing time, whether our models are missing light, or whether our story is missing a chapter we have not learned to read. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin with the light that seems out of place, then trace how Webb measures time in red, and why the Big Bang model sets a specific schedule. From there, we open the case files, test the fastest ways to build galaxies, question the cosmic ruler, and explore what before could even mean. A new deep field image arrives from the James Webb Space Telescope, and it feels like a dare. The frame is almost black at first glance, yet it is crowded with faint structure. In the darkness sit tiny red smudges, pinpricks and soft commas of light that may be entire galaxies. Some candidates look like they come from more than 13 billion years ago. That would place them in a universe only a few 100 million years old, when the first long-lived stars were still rare. This is the promise we sold ourselves when we built Webb, and it was never a modest promise. If you can see far enough, you see back far enough, because the universe keeps its own receipts. The earliest light should show a cosmos still assembling its first structures, small, irregular, and fragile. The problem is that some of these objects do not look like beginners. They look bright, concentrated, and strangely self-assured, as if the early universe skipped a few steps. To understand the shock, we have to clarify what it means to look back in time. Light does not arrive instantly, even across the solar system, where minutes matter. Across the universe, travel times become a record of history, and that record is unavoidable. Every photon is a timestamp, stamped at emission and delivered long after, carrying information about the conditions that created it. When we observe a distant galaxy, we are not seeing it as it is. We are seeing it as it was before the Milky Way had fully settled into its present shape. Distance in cosmology is not just mileage, because space itself expands while light is in flight. This was one of the great 20th century revelations, built from Einstein's general relativity and confirmed by Edwin Hubble's measurements of receding galaxies. As the universe expands, it stretches the wavelengths of travelling light, like ink lines drawn on an inflating balloon. That stretching shifts light toward the red into longer wavelengths, and it also dilutes the light's energy. We call that redshift, and it is our primary clock for cosmic epochs, an elegant idea with sharp edges. Higher redshift generally means earlier times, because the light has been travelling longer through an expanding cosmos. It also means the universe has expanded more since the light left, so the wavelength has been pulled farther from its original value. In practice, redshift becomes a ladder from nearby galaxies to the first ones, and each rung depends on calibration. Webb was designed to climb that ladder in infrared, where the earliest signals are expected to land. The deeper the field, the more the ladder feels like a cliff. Infrared matters because the earliest starlight is shifted out of visible bands. What began as ultraviolet and optical radiation arrives as infrared photons after billions of years of expansion. Webb collects those photons with extreme sensitivity, cold optics, and stable imaging, so faint sources do not smear into noise. Its mirror area and low background are not just engineering triumphs. They are the difference between absence and evidence. Then astronomers translate colours and brightness into physical stories, using models that connect measured light to real populations of stars. In the standard picture, the first few 100 million years are a rough construction phase. Gas cools inside dark matter halos and forms the first stars, which then reshape their surroundings with radiation and explosive deaths. Small galaxies merge into larger ones over time, building mass through accretion and collisions. Massive, orderly systems are expected to be rare at the beginning, because gravity needs time to amplify tiny primordial fluctuations. The early universe should look like scaffolding, not finished architecture. Yet early Webb analyses reported candidates that looked too bright for their redshift, and the brightness was not subtle. Some appeared too massive given the short time available to build stars, especially if star formation proceeds at familiar efficiencies. Some showed hints of structure that felt prematurely mature, compact cores, smooth profiles, and colours suggesting substantial stellar populations. Headlines followed, calling them impossibly early galaxies, and the phrase stuck because it captured a genuine unease. The tension is not that Webb saw distant galaxies at all, because that was the mission. The tension is the combination of distance and apparent maturity, which presses on the timeline like a thumb. If the redshifts are correct, the galaxies seem overachieving, assembling too much too quickly. If the galaxies are normal, something about our inference chain may be wrong, and the mistake could be systematic. Either way, the image becomes an argument, and the argument is about how we turn photons into history. That inference chain begins with what Webb actually measures, which is more limited than the public imagination suggests. It measures flux in several infrared filters and sometimes spectra, depending on exposure time and instrument mode. A filter measurement is a carefully weighted count of photons across a band of wavelengths, not a direct label like age or mass. From those data, astronomers estimate redshift, luminosity, and stellar mass, and then they infer formation histories. Each step depends on models and assumptions that can fail quietly, especially when we push beyond the regime where those models were tested. Many early candidates were selected with photometric redshifts, because spectroscopy is expensive in telescope time. That method compares observed colours to template spectra and finds the best match across many possible distances. It is powerful when spectra are unavailable, and dangerous when multiple solutions fit nearly as well. A dusty nearer galaxy can mimic a pristine distant one, because dust reddens light in a way that resembles extreme redshift. Even small photometric uncertainties can move a candidate from record-breaking to merely very distant. Spectroscopy, when we can get it, changes the game by anchoring redshift to specific features. Instead of broad colours, it looks for sharp breaks and emission lines that mark known atomic transitions. Those signatures can confirm distance, but they can also expose imposters that photometry promoted. The difference is like hearing a melody versus seeing a blurred shape of a musical note. Webb's instruments can do both, yet the deepest fields often begin with photometry because it is the quickest way to sift the sky. Even when redshift is right, brightness is not a direct measure of mass. A galaxy can be bright because it is forming stars intensely, producing many short-lived luminous stars that dominate the light. It can be bright because an active black hole adds light, especially in the central regions. It can be bright because lensing magnifies it along the line of sight, making a modest system look extravagant. The early universe is not only distant, it is also crowded with ways to fool our intuition. Dust complicates everything because it reshapes a galaxy's spectrum in wavelength-dependent ways. Dust can dim ultraviolet light and re-radiate energy in infrared, shifting where the power appears to live. It can make a younger system look older, or a nearer system look farther, depending on the filters used. It can also hide star formation that changes mass estimates, because the missing ultraviolet light is not always recovered in the observed bands. In deep fields, dust is both a physical ingredient and a source of misclassification. Active galactic nuclei complicate things differently by adding a compact power source that is not starlight. A growing black hole can outshine its host galaxy in certain bands, and it can heat surrounding dust that glows in infrared. If that contribution is misattributed to stars, inferred stellar mass inflates, sometimes dramatically. The galaxy looks heavy when it is only loud, and the early universe suddenly seems filled with giants. The question becomes whether we are seeing stellar assembly or black hole-driven glare. Gravitational lensing adds another layer of uncertainty, and it is built into relativity itself. Mass between us and the galaxy bends light and boosts apparent brightness, sometimes stretching sources into arcs and sometimes leaving them deceptively compact. A modest galaxy can masquerade as a giant when magnified, especially if the lensing mass is subtle or poorly mapped. Without careful lens modelling, the early universe can look more crowded with monsters than it truly is. Even a small magnification factor matters when we are counting the rarest objects. Stellar population models are another suspect, because they convert light into mass by assuming how stars are born and evolve. Those models assume an initial mass function and stellar evolution tracks, which determine how much light a given mass produces. They assume metallicity histories and dust attenuation laws, because chemical enrichment changes stellar colours and lifetimes. Small changes can shift inferred masses by factors that matter, especially when we're debating whether an object is merely surprising or fundamentally inconsistent. In the early universe, the stars may not behave like the stars we calibrated on nearby galaxies. Star formation efficiency is also under scrutiny, because it sets the pace of early growth under the same basic physics. If early galaxies converted gas into stars more efficiently, they could build mass faster, even within a few 100 million years. If feedback was weaker, starbursts could last longer before winds and radiation shut them down. The standard timeline might be too conservative, tuned to later galaxies that live in different environments. The deeper question is whether our typical galaxy is a poor guide to the first ones. Behind all of this sits the scaffolding of the Big Bang model, which is both robust and testable. It predicts a hot, dense early phase and a specific expansion history, constrained by the cosmic microwave background and the abundance of light elements. It predicts how quickly structure should grow from tiny fluctuations, as dark matter collapses and baryons follow. If Webb is exposing a mismatch, the fix could be local or profound, and the difference matters. Are we correcting a measurement pipeline or rewriting an early chapter of cosmic history? One possibility is simple, and it would be a relief. Our distance estimates could be off for many candidates, and spectroscopy will sort them, one by one, into their proper epochs. Another possibility is subtler, and harder to see in a single plot. Our mass and age inferences could be biased by templates built on nearby galaxies, whose dust, metallicity, and star formation patterns may not apply. The universe may be doing something ordinary, while our translation scheme makes it sound extraordinary. A third possibility is more unsettling, because it targets early structure formation itself rather than our bookkeeping. Maybe dark matter halos assembled earlier than expected, or baryons cooled faster in dense, pristine environments. Maybe the first stars were different, producing more light per unit mass, so brightness does not imply the same stellar weight. The early universe might be more efficient than our simulations, not by magic, but by conditions we underestimated. If so, Webb is not breaking the timeline, it is revealing its true pace. And there is a fourth possibility that keeps theorists awake, because it touches the cosmic clock itself. If expansion history differs from what we assume, redshift may not map cleanly to time in the way we casually narrate. If new physics alters the early energy budget, structure could grow differently without changing what we observe today. In the extreme, the beginning might not be a single clean event, but a more complex transition with hidden parameters. When the clock is questioned, every timestamp becomes negotiable. This documentary follows the evidence, not the headlines, because the headlines are optimized for astonishment. We will track how Webb data become claims about age and mass, and where the uncertainties enter. We will examine where photometric redshifts break, and why spectra matter when the stakes are record distances. We will test dust, black holes, lensing and modelling choices against the same photons, using consistency rather than excitement as the judge. The goal is not to protect a theory. The goal is to understand what the light is actually saying. We will also ask what it would mean if the anomaly survives every correction, and that question is not rhetorical. Would the Big Bang need revision, or only its early chapters, where we have the fewest direct observations? Would we be seeing the first galaxies, or misreading their light through assumptions borrowed from the local universe? The stakes are the story of origins, and the reliability of our cosmic clock, which underwrites almost every timeline we tell. When a clock is uncertain, even a beautiful image becomes a puzzle. For now, the universe offers a simple provocation. Ancient light reaches us, and it looks strangely confident, bright enough to challenge our expectations, and red enough to imply extreme distance. Either the light is not as ancient as we think, or the early universe grew up fast, assembling luminous systems at startling speed. In the next chapter, we start with the clock itself and ask how time is measured in red. Webb's deep fields look like a direct window into cosmic infancy, yet the telescope does not deliver ages or origins. It delivers photons, counted in bands, shaped by optics, and filtered through inference, so the story is always a translation. In the images, the darkness is not empty. It is a measured background, a calibrated floor, and a field of faint possibilities. Pinpricks of light sit at the edge of detectability, where a single assumption can tilt the interpretation. The mystery is not whether Webb sees something real, but how we decide what the something is. To judge the "too old, too soon" claim, we first demystify the instrument that gathers the light. Then we demystify the methods that translate that light into redshifts, ages, and masses. Webb was built around a simple logic, refined over decades of infrared astronomy and hard engineering lessons. Early galaxies are faint, and their light is shifted into infrared by cosmic expansion, so you need a large mirror, cold optics, and a stable thermal environment. The primary mirror is 6.5 meters across, made of segmented hexagons that act as one surface. More area means more photons collected, and that matters when sources sit near the noise floor for hours. In visual terms, the mirror is a golden mosaic, each segment catching starlight like a quiet metallic petal. When the observatory points, that mosaic must behave like a single flawless bowl. If it does not, the universe blurs. Segmentation is not a gimmick, and it is not merely a packaging trick for launch. It is how a mirror this large fits inside a rocket fairing, then unfolds and aligns in space with millimeter-scale choreography. Alignment is controlled with actuators that adjust each segment's position and curvature, including tiny tilts and piston-like shifts. The goal is a sharp point spread function, because blur turns faint galaxies into background and hides structure. That sharpness is not cosmetic, because deep fields are crowded with barely separated sources. If the point spread function widens, neighbouring galaxies bleed together, and the photometry becomes a negotiation. The instrument's geometry becomes part of the astrophysics. Infrared sensitivity is not only about collecting light, because the telescope itself can become a source. Warm telescopes glow in infrared, and that glow can drown the sky like fog in a night scene. Webb operates cryogenically, with its instruments and optics kept extremely cold to suppress thermal emission. Cold optics reduce background and increase contrast, which is the difference between a detection and a non-detection. At these wavelengths, the physics is simple in principle and unforgiving in practice. Any object above a few tens of Kelvin radiates strongly in the infrared, and detectors cannot tell whether photons came from a galaxy or a warm bolt. The observatory has to be quiet. The sun shield is part of the detector, even though it never touches the light path directly. It blocks sunlight and earthlight, and it creates a stable thermal gradient across the observatory, hot on one side, cold on the other. In animation, the shield looks like a silver kite the size of a tennis court, layered and tensioned in space. Each layer reflects and re-radiates heat outward, stepping the temperature down like a staircase. On the cold side, the telescope can listen. Webb sits near the Sun, Earth L2 point, about 1.5 million kilometers from Earth, in a slow orbit around that gravitational balance. L2 keeps the Sun, Earth, and Moon on one side, making shielding and temperature control simpler and more consistent. This location also stabilizes the observing rhythm, because the telescope can keep its shield oriented while scanning different patches of sky. The result is long, uninterrupted exposures where faint photons accumulate steadily. Deep fields are built from patience. Thermal stability is not comfort, and it is not a luxury reserved for engineers. It is calibration, because drifts in temperature change detector behavior and optical alignment, and those changes can masquerade as astrophysical signals. Even subtle shifts matter, because infrared detectors have complex responses, including persistence and time-dependent noise. A stable environment makes those behaviors predictable, and predictability is what calibration really means. Without it, the faintest galaxies become ambiguous. With the engineering in place, the next step is the cosmic reason infrared matters. The universe expands while light travels, and that expansion stretches wavelengths as space itself grows. A photon emitted in ultraviolet or visible light can arrive billions of years later as infrared. The higher the redshift, the farther the spectrum slides toward longer wavelengths, and the more the original colours are rearranged. Redshift is defined by how much the wavelength has stretched compared to its emitted value. In the standard model, that stretch maps to distance and to look-back time, because expansion has a measured history. That history is not guessed from one observation, because cosmology is a stitched fabric of evidence. It draws on the cosmic microwave background, galaxy clustering, and supernova distances, which together constrain how fast the universe expanded at different epochs. Webb plugs into that framework. This mapping is the clock behind every first galaxy headline, and it is easy to forget that it is a derived clock. If the clock is misread, the entire story shifts, even if the photons are real. When we say look back time, we are describing a layered view, not a simple rewind. Light left a galaxy when the universe was smaller, denser, and chemically younger, and it travelled through intervening gas that can imprint its own signatures. The path matters. Webb measures flux through filters that cover different infrared bands, each one a carefully engineered window. Each filter gives one number, an integrated brightness across a wavelength range, with uncertainties that grow at the faint end. Put several filters together and you get colours, which are ratios of fluxes between bands. Colours are crude spectra, and crude spectra can still reveal strong breaks when the physics produces a sharp edge. In a deep field montage, those colours become a kind of code, where a galaxy brightens in one band and disappears in another. The disappearance is not absence, but a clue. It suggests that something in the spectrum has moved. The most famous break for early galaxies is the Lyman break, rooted in atomic hydrogen and the structure of electron energy levels. Neutral hydrogen absorbs photons bluer than the Lyman limit, cutting off flux shortward of 912 angstroms. At high redshift, that cutoff is shifted into infrared filters, where Webb's sensitivity is strongest. A galaxy can appear in redder filters and vanish in bluer ones, creating a dropout that looks dramatic in the data table. The dropout method is powerful because it works when spectra are unavailable, and it can be applied to thousands of sources quickly. It is also vulnerable, because several different physical situations can mimic the same colours when information is limited. A dusty galaxy at lower redshift can look red and faint in blue bands because dust grains preferentially absorb and scatter shorter wavelengths. An old stellar population can also suppress blue light, producing a false impression of extreme distance. Strong emission lines can create another trap, because galaxies are not smooth continua. If a line falls inside one broadband filter, it can boost that filter's flux and fake a sharp colour change. Even noise can promote imposters, and the effect is subtle but persistent in large samples. Near the detection limit, random fluctuations can erase a faint signal in one band and exaggerate it in another, producing a dropout by chance. This is where photometric redshifts enter, and where the translation becomes explicitly statistical. A photometric redshift is an estimate derived from multi-filter colours matched to template spectra across many redshifts. The algorithm searches for the best fitting template and returns a probability distribution, not a single truth. The peak can look decisive, even when a second solution is nearly as good and physically plausible. Those templates encode assumptions about stellar populations, dust, and emission lines, which means the method inherits the model's blind spots. Photometric redshifts are fast and scalable, which is why early surveys lean on them. They are also model-dependent, which is why early claims often soften later. There is also a historical echo here, because astronomy has repeatedly advanced by pushing into regimes where spectroscopy lags behind imaging. From early photographic plates to the first CCD surveys, catalogues came first, and confirmations followed. Webb repeats that pattern at a new frontier. Spectroscopic redshifts are different, because they measure structure within the light rather than only its integrated colours. Spectroscopy spreads the light into many narrow wavelength bins, revealing features that can be tied to known atomic transitions. A single identified line can anchor a redshift if the line identity is secure, but line identity is sometimes the hardest part. Multiple lines or a clear break can lock the solution and collapse ambiguity, turning a candidate into a measurement. Webb's spectrographs can confirm candidates, but spectroscopy costs time, and time is the currency of deep space observatories. Deep spectroscopy competes with the desire to survey many objects quickly, especially in the first years. This trade-off shaped the first wave of headlines, because the community wanted to map the landscape rapidly. Photometric candidates appeared first, and spectroscopic confirmations arrived later, sometimes revising distances downward. The revisions were not failures, but refinements. To see why, we need the specific features astronomers look for in the earliest galaxies, and why those features can hide. Some are breaks from absorption, and some are emission lines from hot gas lit by young stars. Lyman alpha is a key line in principle, produced when electrons in hydrogen drop to the ground state after being excited. In practice, Lyman alpha is often absorbed by neutral hydrogen, so the line can be faint or absent. Inside a galaxy, dust and gas can scatter and absorb Lyman alpha, forcing photons into long wandering paths that increase the chance of destruction. Outside the galaxy, the intergalactic medium can erase it, especially before ionization completes, and neutral hydrogen is common. That absence is itself informative because it hints at the state of the surrounding universe. If Lyman alpha is missing, astronomers look for other anchors that are less easily erased by intervening gas. The spectrum offers alternatives. The Balmer break is one, created by the accumulated light of older stars around 3646 angstroms and shaped by stellar atmospheres. A strong Balmer break can suggest a more evolved stellar population, though it can be mimicked by other effects. At high redshift, the Balmer break shifts into infrared bands where Webb has strong coverage, and where the photometry can sample both sides of the feature. In visuals, it is a step in the spectrum, a quiet cliff rather than a spike. That step can be persuasive. Emission lines from ionized oxygen and hydrogen are also central, because young galaxies can be dominated by glowing nebulae. O3 and H-beta can be extremely strong in metal-poor star-forming regions, where hard ultraviolet radiation excites the gas efficiently. Ch-alpha is another workhorse line, often the brightest recombination line in star-forming galaxies, and it traces the presence of massive, short-lived stars. At high redshift, it moves into longer infrared wavelengths, sometimes beyond the most commonly used filters. These lines matter because they can contaminate broadband photometry, and broadband filters are blunt instruments by design. A filter does not know whether its photons came from continuum starlight or from a narrow line. It only counts. If O3 or H-alpha boosts a band, the galaxy can look brighter and redder than its stellar continuum would imply. That can inflate inferred stellar mass and age, because the model attributes extra light to more stars rather than to a line. Line contamination can also distort photometric redshifts, because a boosted band can mimic the colour signature of a break. The fitting code may push the best fit solution to higher redshift, even though a lower redshift line-rich galaxy fits nearly as well. Once redshift is estimated, the next translation step is SED fitting, where the goal is to infer physical properties from limited data. The spectral energy distribution is the galaxy's brightness as a function of wavelength, sampled at discrete filter points. Said fitting compares observed photometry to synthetic galaxy models, which are built from stellar evolution calculations and libraries of spectra. The models combine stellar populations, dust attenuation, and nebular emission to reproduce the measured colours within stated uncertainties. From that match, astronomers infer stellar mass, star formation rate, dust content, and characteristic age, often with impressively small-looking error bars. These outputs are not direct measurements, and they are not immune to hidden assumptions. They are model-dependent inferences. The mass estimate depends on the mass-to-light ratio in the model, which changes with age, metallicity, and the assumed distribution of stellar masses. A small change in assumed stellar population can change mass by factors that matter for two massive claims. The same photons can imply different weights. The age estimate depends on how the model treats star formation history, and history is rarely smooth in real galaxies. A bursty history can mimic an older population if the recent burst dominates the light, while older stars hide in the background. Light remembers the last fireworks. Dust adds degeneracy, because it reddens and dims light in a wavelength-dependent way. Reddening can be confused with age or with higher redshift when the data are sparse, especially if only a few filters bracket the key breaks. The spectrum can be bent in more than one way. Nebular emission adds another degeneracy, because ionized gas produces lines and continuum that reshape colors. This can mimic a strong break, especially when lines fall into key filters that define the dropout selection. What looks like a cliff may be a spike. Metallicity is a quiet lever, and it evolves as galaxies enrich themselves with heavy elements from supernovae. Low metallicity stars are bluer and can be more luminous per unit mass, shifting inferred ages and masses for the same photometry. A chemically young galaxy can look deceptively bright. The initial mass function is another lever, and it is rarely visible in the final plot because it is usually assumed rather than measured. If early stars formed with a different IMF, the light-to-mass conversion changes, and so does the inferred assembly speed. A top-heavy IMF would produce more luminous, massive stars, lowering the mass needed to explain a given brightness. A bottom-heavy IMF would do the opposite, hiding mass in faint, long-lived stars. Either way, the same image can imply different histories. Dust attenuation laws are also assumptions, not facts, and different laws reflect different grain properties and geometries. Different laws change how much ultraviolet is suppressed relative to infrared, shifting inferred star formation rates, and sometimes shifting preferred redshifts. The curve you choose matters. Star formation histories are often simplified because the data cannot constrain everything, especially for the faintest sources. Exponentially rising or declining forms can bias ages when reality is episodic, with pauses, bursts, and feedback-driven cycles. Simplicity can be a hidden prior. Even the choice of priors matters, because Bayesian fitting rewards what it is allowed to consider plausible. If the fitting code is allowed to prefer older ages or higher dust, it can steer solutions toward mature interpretations. The output can reflect the question's framing. Systematics do not mean the results are wrong, and they do not imply that the early universe is being misread on purpose. They mean the error bars are not only statistical, and the uncertainty can be correlated across many galaxies in the same survey. A shared assumption can shift a whole population. Calibration and background subtraction also matter at the faint end, where the sky is a measured quantity rather than a given. Small biases in sky estimation can shift fluxes, and flux shifts can move redshift solutions, especially when a single band drives the dropout. The background is part of the data. Crowding adds another risk, because deep fields pack sources into small angular areas, and the point spread function spreads light across pixels. Deblending algorithms must decide how to assign photons to neighbors, and those decisions can change colors. In crowded scenes, identity is negotiated. Lensing can quietly amplify brightness, even when no dramatic arc is visible, because mass bends light in subtle ways. If magnification is not recognized, luminosities and masses are overestimated, and a galaxy can seem unusually powerful for its supposed age. Gravity can masquerade as growth. Active nuclei can also bias the translation, because an accreting black hole can add a hot continuum and strong lines. The SED fitter can misread that as starlight, inflating star formation rates or altering inferred ages. A tiny central engine can dominate the light. Each of these effects can push in the same direction, and that is why the too old, too soon tension can feel sudden. They can make a galaxy look farther, brighter, older, or more massive than it truly is, especially when several biases align. The edge of the map is where mirages form, yet the opposite can also happen, and it is worth holding that symmetry in mind. Some assumptions can hide mass by underestimating dust, or hide age by overemphasizing recent star formation, making early galaxies seem less mature than they are. Uncertainty cuts both ways. The point is not that inference is hopeless, because the methods are grounded in physics and tested across many regimes. The point is that Webb's early galaxy claims sit at the edge of the calibrated regime, where multiple explanations compete and where confirmation is slow. So we return to the central question with sharper tools and a more cautious sense of what the data truly say. Are mature early galaxies exposing a flaw in measurement and modelling, or hinting the Big Bang was not the absolute beginning? The question hangs because the translation is delicate. The telescope is not the controversy, and the photons are not the argument. The translation from photons to properties is where the story can bend, and where careful confirmation changes the narrative. In science, the drama often lives in the pipeline. Once we understand how Webb converts faint infrared light into redshifts, ages, and masses, we can ask why the translated story sounds too old, too soon. The next step is to interrogate the clock and the assumptions that make it feel certain. Webb's deep fields forced a question about translation, but translation depends on a timeline that everyone agrees to use. Before we judge any too early galaxy, we have to set the standard clock. In practice, that clock is not a wristwatch or a calendar. It is a model of expansion, calibrated by multiple independent cosmic measurements. Modern cosmology uses a working model called LCDM, pronounced lambda, cold dark matter, and it functions like a shared set of rules. It says the universe expands from a hot, dense beginning, then cools and grows structure under gravity. In the visuals, imagine a smooth, bright fog swelling outward, while tiny ripples in density slowly deepen into a cosmic web. LCDM is not presented as a philosophical statement about origins, but as a quantitative framework that predicts what we should see. It links the geometry of space, the contents of the universe, and the growth of structure into one consistent story. When observers say too early, they're really asking whether the story's pacing can still match the data. In this framework, ordinary matter is a minority component, even though it is the part that shines and forms planets. The atoms in stars, dust, and people add up to only a small fraction of the cosmic energy budget. Most matter is cold, dark matter, which clumps gravitationally but does not emit light, and so it reveals itself only through its pull. Cold is a technical word here, meaning the particles move slowly enough to clump on small scales early on. If dark matter were hot, moving near light speed, it would smear out tiny structures and delay galaxy formation. LCDM assumes cold dark matter, precisely because the universe contains abundant small-scale structure, from dwarf galaxies to the fine filaments traced by larger ones. The other dominant ingredient is dark energy, written as L, a term that echoes Einstein's cosmological constant. It drives accelerated expansion at late times, stretching distances and slowing structure growth as the universe ages. Visually, you can picture the grid of space itself relaxing outward, subtly at first, then with growing influence as matter thins. LCDM is not a single guess, and it is not built from one dataset or one telescope. It is a stitched fit to many measurements that agree surprisingly well, even though they probe different eras. The model has survived because it makes the same universe explain the oldest light, the distribution of galaxies, and the present expansion rate. The cosmic microwave background is the anchor point, and it is often described as the universe's baby picture. It is relic radiation released when the universe first became transparent, carrying information from a time before any star existed. On screen, it appears as a mottled sphere of faint microwaves, a nearly uniform glow with delicate speckling. That moment is called recombination, about 380,000 years after the Big Bang, when temperatures fell enough for electrons to bind to protons. Electrons and protons combined into neutral hydrogen, and photons finally travelled freely instead of scattering constantly. The universe went from an opaque plasma to a vast, dimly lit expanse, like fog lifting to reveal a horizon. The CMB is not just a glow, it is a map of tiny temperature variations across the sky. Those variations are the fossil record of primordial density fluctuations, imprinted when the universe was still extremely young. Each slightly warmer or cooler patch corresponds to regions that were a little denser or thinner than average. The fluctuations are small, about 1 part in 100,000, and that smallness is part of the mystery. LCDM treats them as the seeds that gravity later amplifies into galaxies' clusters and the web-like scaffolding between them. A tiny early imbalance, given enough time, becomes a dramatic difference in what eventually forms. Those CMB ripples also encode sound waves in the early plasma called acoustic oscillations, frozen into the pattern we measure today. They set a characteristic scale that later reappears in the distribution of galaxies, like a faint echo across billions of years. The clock begins with that imprint, because it fixes both the starting conditions and the overall composition. From recombination, the universe enters the Dark Ages, a period named for the absence of starlight rather than the absence of activity. There are no stars yet, and neutral hydrogen fills space, absorbing energetic ultraviolet light. In imagery, the cosmos is a black ocean with invisible currents, matter moving, collapsing and heating, but not yet igniting. During the Dark Ages, dark matter continues to collapse into halos, the gravitational wells that will host galaxies. Baryonic gas falls into those potential wells, but it must cool before forming stars, and cooling is not automatic. Gas that cannot shed energy stays puffy and pressure-supported, resisting collapse even inside a halo. Cooling depends on what the gas is made of and how it can radiate energy away. In the early universe, there are almost no heavy elements, so the gas lacks many efficient cooling channels. Molecular hydrogen can help, but it forms only under certain conditions, and it can be destroyed by ultraviolet light from the first stars. The first stars are expected to be population 3, a label that reflects a historical ordering of stellar generations. They form from pristine hydrogen and helium, with almost no heavy elements to aid cooling and fragmentation. Because the gas cannot easily break into many small clumps, theory predicts the first stars skew massive. These early stars are predicted to be massive and short-lived, burning their fuel at a furious rate. They flood their surroundings with ultraviolet radiation and explode as the first supernova, seeding their neighborhoods with the first metals. In a visual sequence, one can imagine isolated points of blue-white light turning on in the darkness, then ending in brilliant, expanding shells. Those first sources begin reionization, a long transition when ultraviolet photons ionize the neutral hydrogen fog. The universe becomes progressively more transparent to UV light, as electrons are stripped from atoms again. It is a strange reversal. After recombination made atoms neutral, the first light sources undo that neutrality on intergalactic scales. Reionization is not a single switch, and it is not uniform everywhere, because galaxies do not form everywhere at once. It is a patchwork process that depends on how many early galaxies form, how bright they are, and how easily their photons escape. Picture bubbles of ionized gas expanding around early galaxies, then merging into larger regions as the bubbles overlap. By roughly 1 billion years after the Big Bang, most intergalactic hydrogen is ionized, and the fog thins dramatically. After that, ultraviolet light travels farther without being erased, and the universe becomes more transparent to certain spectral signatures. The end of reionization is not a clean line, but it is a milestone that affects what we can observe. This sequence is the standard narrative, but the key is the pacing, because the early universe offers very little time. LCDM predicts a gradual build-up of structure, not instant maturity, because gravity needs time to amplify small fluctuations. The model's success depends on the idea that complexity emerges step by step, not all at once. Structure formation begins with the CMB fluctuations and proceeds through gravitational growth, a process that is slow at first and faster later. Overdense regions attract more matter, and the contrast increases with time as the densest regions grow denser. The cosmic web is the result: filaments, nodes, and voids arising from tiny beginnings. Cold dark matter matters because it starts clumping early, even when ordinary matter is still coupled to radiation. It does not feel radiation pressure the way ordinary matter did before recombination, so it can begin building gravitational wells sooner. In effect, dark matter lays down invisible scaffolding that gas will later fall into. In LCDM, dark matter halos form first, then gas follows, pulled inward by gravity and slowed by pressure. Stars form after gas cools, fragments and collapses inside those halos, and each step adds delay. That ordering is not just narrative convenience, it is enforced by thermodynamics and by the finite speed of physical processes. This ordering creates a built-in delay between halo growth and stellar mass growth, and that delay is central to two early claims. The earliest galaxies should be small because the earliest halos are small, and because their gas has had limited time to cool. Even if a halo forms early, turning its baryons into stars still takes time. As time passes, halos merge and accrete, and the merger tree becomes more complex with every generation. Small systems combine into larger ones, and galaxies grow through both mergers and fresh inflow along filaments. On screen, you might see faint knots of matter drifting together, then snapping into tighter orbits as gravity binds them. The model does allow rare early peaks, because the primordial fluctuations include statistical outliers. A few halos can collapse unusually early in the highest density regions, but their numbers are tightly constrained by the initial fluctuation spectrum. In other words, LCDM permits early giants, yet it also predicts they should be exceptional, not common. Those constraints are summarized by the halo mass function, a statistical forecast for how many halos of a given mass exist at each redshift. It is derived from the growth of fluctuations and tested against simulations and large-scale surveys. The function is not merely descriptive, it is a quantitative boundary line for what counts as plausible. At very high redshift, the mass function falls steeply at the high mass end, which means the universe should contain far fewer massive halos early on. Extremely massive halos are possible in principle, but statistically scarce, like rare peaks in a rough landscape. When observers infer many massive galaxies early, they are implicitly claiming many rare peaks. This is where too massive, too early becomes a quantitative claim, rather than a reaction to something that looks impressive. It is not about one bright object, but about populations that are too common given the predicted rarity of their host halos. A single anomaly can be chance, but a whole crowd demands an explanation. If Webb finds many very massive galaxies at very high redshift, the implied halo population may exceed LCDM expectations, and that would signal tension with the growth rate. It would suggest either that structure formed faster than predicted, or that our mapping from light to mass is biased. The mystery, then, is whether the universe is breaking the rules, or whether we are misreading the scoreboard. Yet galaxies are not halos, and the mapping is uncertain, especially when we rely on limited photometric bands. To turn halo mass into stellar mass, we need a star formation efficiency, and we need assumptions about stellar populations. We also need to know how much light is coming from stars versus other sources, and how dust reshapes what escapes. Efficiency is the fraction of available baryons converted into stars, and it is bounded by the cosmic baryon fraction. In the local universe, it is limited by feedback, turbulence, and heating, which prevent gas from collapsing smoothly. Supernova explosions, stellar winds, and radiation pressure can all blow gas out or keep it hot. In the early universe, efficiency could differ because gas densities are higher and inflows can be more intense. But it cannot exceed physical bounds, because a galaxy cannot turn more than its baryon budget into stars. If an inferred stellar mass demands more baryons than the halo can plausibly contain, the inference is signaling a problem. It also cannot convert gas into stars instantly, because cooling, fragmentation, and feedback impose timescales that cannot be cheated. Even extreme starbursts have limits, set by how quickly gas can be supplied, and how violently young stars disrupt their own nurseries. The early universe may be efficient, but it is not magical. So impossible has a specific meaning in this story, and it is narrower than surprising. It means inferred stellar masses that require unphysical efficiencies, or number counts that break the halo mass function in a statistically robust way. It also means assembly histories that cannot fit inside the available time, even with aggressive assumptions. It also means ages that leave no time for assembly, because stars cannot be older than the universe that contains them. A galaxy that appears to contain billions of solar masses in old stars at extreme redshift strains the clock. The tension is not aesthetic, it is a mismatch between inferred histories and the maximum time allowed. That clock is set by the expansion history, which is why cosmologists treat redshift as more than a color shift. Redshift is a measurement tied to how the universe expanded over time, stretching wavelengths as space itself expands. When we measure a redshift, we are not just measuring distance, we are placing an object on a timeline. The Hubble parameter describes the expansion rate, and in LCDM it changes with epoch in a predictable way. It is shaped by radiation early, then matter, then dark energy, with each component dominating at different times. The early universe expands rapidly, but it also evolves rapidly, and that combination compresses the early timeline. Because the expansion rate evolves, the age of the universe at a given redshift is calculable, once the model parameters are fixed. High redshift corresponds to a surprisingly small amount of elapsed time, even if the distances involved feel enormous. The deep field may look like a static image, but it is a layered stack of eras. For a galaxy at redshift 10, the universe is only a few 100 million years old, depending on the exact cosmological parameters. That is the entire budget for forming stars, metals and structure, including the time needed for gas to cool and for halos to assemble. When we say early, we mean early in a brutally constrained schedule. This is why Webb's candidates feel provocative, even before any dramatic conclusion is drawn. If their redshifts are correct, their apparent masses and brightness must fit inside that narrow window, and the window is not negotiable without changing the expansion history. The clock turns a pretty picture into a physics test. Rionization adds another constraint that intersects with brightness, because it controls what kinds of photons can travel freely. Before rionization completes, neutral hydrogen absorbs ultraviolet photons and suppresses certain spectral features. The intergalactic medium acts like a filter, and the filter's strength depends on how ionized the universe is in that region. Lyman alpha emission is especially vulnerable, because it resonates strongly with neutral hydrogen and is easily scattered or absorbed. A bright early galaxy might still show weak Lyman alpha if the surrounding intergalactic medium is neutral. That absence is not necessarily evidence against the galaxy. It can be evidence about the fog between us and it. So early brightness can be consistent with a neutral universe, but it also raises a demand that cannot be ignored. Enough early galaxies must exist, and must leak enough ultraviolet photons to drive reionization on schedule. If the early universe is full of luminous systems, then the ionized bubbles should grow quickly and overlap sooner. If Webb implies many luminous galaxies very early, reionization could happen faster than expected, changing how we interpret other data sets. If it implies too few, reionization becomes harder to explain, and we must ask what other sources contributed. Either way, the timing matters because it is cross-checked by independent observations. CMB polarization measurements constrain the integrated optical depth, which is sensitive to how much free electron fog the CMB photons pass through. Quasar absorption spectra, especially the Gunn-Peterson trough, show how neutral hydrogen persists at later times. Together they bracket the reionization story, turning it into another clock face on the same wall. LCDM therefore sets multiple clocks at once, and they are designed to agree with each other. The CMB sets the initial conditions, the halo mass function sets growth statistics, and reionization sets transparency timing. When a claim challenges one clock, it often touches the others, whether we intend it or not. A faster early build-up changes the ultraviolet budget, the metal enrichment rate, and the expected clustering of early galaxies. More early stars mean more supernovae, more dust, and more heavy elements, which then alter cooling and later star formation. The early universe is a coupled system, so a change in one place echoes across the timeline. This is why cosmologists treat Webb's early galaxy puzzle as a system problem, not a single object mystery. The question is not only whether one object is odd, but whether the whole network stays consistent when we add the new data. The deeper question is almost philosophical. How many independent clocks can disagree before we admit the model needs revision? There are also ways to relieve tension without breaking LCDM, and they mostly involve how we infer mass and age from light. If stellar populations are more luminous per unit mass, masses drop for the same brightness, and the galaxies become easier to fit. That could happen if the initial mass function is top-heavy, or if young stars dominate the light. If strong emission lines boost broadband fluxes, photometry can overestimate stellar mass, because the galaxy looks brighter in certain filters. In that case, the continuum light from stars is being contaminated by line emission from ionized gas. A spectrum can separate these contributions, but a few photometric points can blur them together. If an active nucleus contributes light, the galaxy can look heavier than it is, because accreting black holes can be extraordinarily luminous. The nucleus can mimic the colours of stellar populations, especially when data are sparse and templates are imperfect. The result is not deception by the universe, but an honest limitation of inference. If lensing magnifies sources, number counts and luminosities can be biased upward because a foreground mass acts like a natural telescope. A small background galaxy can be stretched and brightened, and it can be pushed above detection thresholds. Even mild lensing spread across many sightlines can subtly inflate the apparent abundance of bright objects. If dust and templates mislead redshift estimates, the timestamp itself can shift, because colours can be mimicked by different combinations of age and obscuration. A dusty, moderately distant galaxy can sometimes masquerade as a pristine, extremely distant one in broadband photometry. That is why spectroscopy is so prized. It pins the redshift to specific features. But the chapter's point is the baseline expectation, because without a baseline there is no meaningful surprise. Under LCDM, the first galaxies are expected to be small, rapidly forming, and statistically rare at high mass. They should appear as compact knots of star formation, embedded in a universe that is still becoming transparent. The model predicts a hierarchy of assembly, and that hierarchy is the story's spine. Tiny fluctuations grow into halos. Halos gather gas, gas-form stars, and galaxies build up through time as mergers and accretion continue. The universe is not expected to skip steps, because each step depends on the one before it. Webb appears to show systems that look bright, compact, and abundant earlier than that hierarchy suggests, and the images invite a double-take. The tension lives in the gap between predicted pace and inferred maturity, between what the clock allows and what the light seems to imply. The mystery is sharpened by how calm the LCDM timeline looks on paper, compared with how exuberant the early candidates appear. To understand that gap, we need to keep the standard clock visible in every frame of the argument. Every redshift implies an age, every age implies a growth budget, and every budget implies limits on mass, metals, and luminosity. The deep field becomes a ledger, and the question becomes whether the numbers can balance. Now the clock is set and the mystery sharpens. Are these galaxies truly early, or are we misreading the timestamp? In the next chapter, we test the evidence against the clock, because extraordinary claims in cosmology live or die on calibration. We ask where the redshifts come from, how secure the distances really are, and what assumptions are hidden inside the translation from colour to mass. And we ask, quietly but directly, whether the early universe is being dated correctly, or whether the clock itself needs to be rechecked. Now the clock is set, and the mystery sharpens into a set of case files. Webb's first deep fields did not just add distance, they added volume, sensitivity, and a sudden crowd of faint red sources. On screen, the view is almost austere. Black sky, scattered points, yet the statistics underneath feel loud. Those early datasets were small in sky area, yet deep enough to expose a new regime. In a few pointings, Webb reached flux levels where previous surveys saw mostly noise, because its mirror and infrared instruments were built for exactly this dim light. The result was a catalogue that looked overpopulated with red candidates, as if the early universe had been hiding a surplus. The first interpretation followed a familiar chain of inference, one astronomers have practiced since the Hubble Deep Field era. Red colours suggested a Lyman break shifted far into infrared bands, where intergalactic hydrogen absorbs light blue ward of 1216 angstroms. Photometric redshift codes returned peaks at extreme redshift, sometimes with unsettling confidence, because the best fit template can look uniquely persuasive. Then came the second inference, and it carried the headline weight. Some candidates were bright in the reddest filters, implying high luminosity at enormous distance, where the luminosity distance inflates the required intrinsic power. If that light was mostly starlight, the implied stellar masses rose quickly, and the implied assembly times shrank. In LCDM terms, brightness at high redshift is not just a property. It is a demand on halo rarity, baryon supply, and star formation efficiency, because only a small fraction of matter collapses early into massive halos. A few bright outliers are expected, but a crowd changes the statistics, especially when the survey volume is known. There is also a quiet technical detail behind the drama. At these redshifts, the rest frame ultraviolet is shifted into near-infrared filters, so what looks like infrared brightness is often young, hot star light in disguise. The translation from flux to mass depends on assumptions about stellar populations, metallicity, and dust, and each assumption is a lever. So Chapter 4 treats the claims like clues, not conclusions. Each object becomes a file with competing explanations, and each explanation has an observable fingerprint if we look carefully enough. The suspense comes from how easily a single assumption can flip the story, like turning a page and finding a different suspect. Case File 1 is the photometric candidate that looked too massive. Its infrared flux was read as a strong continuum from many stars, spread smoothly across several filters. The FIT preferred an older population with a high mass-to-light ratio, which is another way of saying a lot of mass for not much light. The inferred redshift placed it within the first few 100 million years. That timestamp left little room for repeated star formation and metal enrichment, because heavy elements must be forged in stars and dispersed by winds and supernovae. The mass estimate then implied an efficiency near the physical ceiling, where nearly every available baryon would have to become stars. That is where the case begins to feel like a courtroom. In LCDM, the cosmic baryon fraction sets an upper budget, and feedback from massive stars and supernovae tends to push gas back out. If a galaxy appears to break those constraints, we either found a rare extreme, or we misread the evidence. But photometry is a blunt instrument, even with many filters. Broadband points can be fit by different combinations of redshift, dust, age, and lines, because each filter compresses a wide range of wavelengths into a single number. Early catalogues therefore carried a hidden warning inside their probability curves, even when the best peak looked crisp. A vivid way to picture the problem is to imagine a spectrum squeezed into a handful of coloured buckets. If one bucket is unexpectedly full, the code must decide whether the whole spectrum is high or whether a narrow feature poured into that bucket. The difference is everything, yet the data can look similar. Spectroscopic follow-up is where the file either closes or deepens. A spectrum can anchor redshift with identifiable features, and it can reveal whether broadband flux was continuum or line, because lines appear as sharp spikes rather than gentle slopes. It can also show that the photometric peak was not the only plausible solution, even when the catalogue seemed definitive. When spectra arrived for some headline candidates, several moved closer than first thought. A lower redshift reduces luminosity distance, and it reduces the implied intrinsic brightness, because the same observed photons travelled a shorter cosmological stretch. The same observed flux then corresponds to a less extreme galaxy, and the halo statistics relax. That revision is not a failure of Webb or of the observers. It is the normal arc of discovery, where early photometric claims map the territory and spectroscopy draws the borders. The deep fields are reconnaissance first and legal testimony later. Other spectra told a different story, and it was more subtle. The redshift stayed high, yet the mass estimate fell, which means the distance was not the main culprit. The culprit was contamination inside the filters, extra light that looked like stars but was actually gas. Nebular emission lines can dominate young galaxies. Ionized gas around hot stars produces O3 and H-beta with enormous equivalent widths, because the gas reprocesses ultraviolet photons into bright optical lines. When those lines land inside a broadband filter, the filter records them as extra starlight, even though the continuum may be modest. This matters because photometric fitting often searches for breaks. A boosted red filter can mimic a Balmer break, which is usually read as evidence for older stars and a more developed stellar population. The code can then assign a high mass-to-light ratio and inflate stellar mass, even when the galaxy is simply line-rich. In the Webb era, O3 and H-beta are frequent suspects. At certain redshifts, they fall into commonly used near-infrared bands, and the exact placement depends on the filter edges and the galaxy's precise redshift. A single line-rich band can pull the fit toward a mature interpretation, like a witness whose testimony is louder than the rest. Once line emission is modelled explicitly, the same candidate can look younger and lighter. The continuum drops, the Balmer break weakens, and the implied stellar mass can fall by factors, sometimes by several times. The headline tension softens without changing the cosmic clock, which is why this case file matters so much. There is a broader lesson in this correction. Early galaxies are often compact, vigorously star-forming systems, and vigorous star formation naturally produces strong nebular lines. In other words, the very youth we expect at high redshift creates the spectral features that can masquerade as age. Case file 2 is the candidate that looked too bright, not just too massive. Its photometry suggested a luminosity that seemed hard to reconcile with early halo statistics, because the bright end of the luminosity function should thin quickly. The question became whether it was truly rare or merely made to look rare. Here, gravitational lensing enters as a quiet accomplice. Foreground mass can magnify background galaxies without producing obvious arcs, because weak lensing can stretch and brighten subtly rather than dramatically. Even modest magnification can push a source above detection thresholds and into a too bright bin. Lensing also biases number counts in a non-intuitive way. If surveys preferentially detect magnified sources, the bright end looks more populated, and the inferred abundance of luminous galaxies rises. Rare objects can seem common, because the selection function has been bent by gravity, an invisible hand shaping the catalogue. Correcting for lensing requires mass models of the foreground field. In blank fields, the lensing is weaker, yet not zero, because every line of sight passes through a web of dark matter and galaxies. Uncertainty in magnification becomes uncertainty in intrinsic luminosity, and that uncertainty propagates into mass and efficiency. Visually, this is the kind of effect that feels cinematic. The background galaxy is a small ember, but the foreground is a transparent lens, warping space without announcing itself. The image looks calm, yet the geometry is doing work behind the scenes. Case file 3 is the candidate that looked too old. Its colours were fit with an evolved stellar population, implying star formation started extremely early, perhaps uncomfortably close to the onset of galaxy formation. The implied age pressed against the available time since the Big Bang, which is a hard boundary set by the expansion history. But age is not observed directly, even with spectra. Age is inferred from spectral shape, and spectral shape is degenerate, especially when the signal to noise is low and the continuum is hard to measure. Dust can redden a young galaxy into looking old, particularly when only a few points bracket the key features. A dusty starburst can imitate a quiescent system. Heavy reddening suppresses blue light, and the remaining infrared flux looks like a red continuum, smooth and deceptively settled. The fit can then choose age when dust would also work, because both solutions can reproduce the same colours. This is the dust and age degeneracy, and it is a central reason early claims diverged. If the templates underrepresent extreme dust at moderate redshift, the code may prefer extreme redshift instead, because a Lyman break can mimic a dust-reddened slope. If the templates over-permit old ages, the code may create maturity where the universe has barely had time. Historical context matters here, because this is not a new trap. Astronomers faced related degeneracies in earlier deep surveys, where red galaxies could be either distant and young, or nearer and dusty. Webb did not invent the ambiguity, it amplified it by revealing many more candidates at once. Spectra help, but they do not always end the argument. A spectrum can confirm redshift while leaving dust and star formation history uncertain, because the continuum shape may still be noisy. It can show lines that imply active star formation, even when photometry suggested an older population, and that contradiction becomes a clue. If strong lines are present, the galaxy is not quietly aging in the dark. It is forming massive stars that ionize gas, and those stars live fast and die young. The spectrum, in that sense, is not just a measurement, it is a timestamp on the current physical state. Case file 4 is the AGN masquerade, and it complicates every other file. An accreting black hole can add a power law continuum and strong lines, and it can do so with a compact source that fits inside a single pixel. It can also heat dust, reshaping infrared colours and making a galaxy look heavier than it is. At high redshift, an AGN can be hard to diagnose. The host galaxy is faint, the nucleus can dominate, and classical diagnostics may fall outside observed bands because the key-rest frame optical lines are shifted. The result can be a galaxy that looks massive because it is bright, not because it has many stars. Separating stellar light from nuclear activity requires multiple clues. Broad emission lines point to fast-moving gas near the black hole, where velocities can reach thousands of kilometers per second and smear line profiles. High ionization lines suggest hard radiation fields that stars struggle to produce, and their presence shifts the interpretation. Yet even narrow-line AGN can hide inside star-forming spectra. In that case, the nucleus boosts flux and alters colours without announcing itself with obvious broad lines. The mass estimate then inherits the contamination, and the galaxy's place in the statistics becomes uncertain. Across these files, a pattern emerges in how anomalies evolve. The first wave is photometric, fast and vulnerable to template choices, because catalogues can be produced quickly from imaging alone. The second wave is spectroscopic, slower, and often corrective, because spectra demand time, calibration, and careful interpretation. Some candidates vanish as high redshift objects when spectra reveal lower redshifts. Some remain high redshift but lose their extreme masses when line contamination is modelled, and that outcome is a quiet victory for patients. Some remain ambiguous because the spectra are too faint for decisive features, leaving the file open with penciled notes. The debate is not only about individual objects, but about populations. If many candidates are revised downward, the tension becomes a story about selection effects, priors, and the hazards of early inference. If a subset remains extreme after corrections, the tension becomes a story about early efficiency and about how quickly gas can turn into stars. This is where the remaining provocation sits today. Even conservative analyses still find luminous galaxies at very high redshift, and they appear in multiple fields rather than a single lucky pointing. Their inferred star formation rates can be high enough to strain typical feedback-limited efficiencies, especially if the systems are compact and rapidly assembling. The strongest remaining claims are careful about language, yet still unsettling. They do not say the Big Bang is disproven, and they do not claim the expansion history is wrong. They say that within the standard clock the early universe may have built stars faster than expected, and that our translation from light to mass may still be incomplete. That conclusion can be framed in several ways, and each has different implications. Perhaps early gas inflows were more intense and less disrupted by feedback, because the first halos were dense and the cosmic web delivered fuel efficiently. Perhaps stellar populations were more UV bright per unit mass than assumed, because low metallicity changes stellar temperatures and lifetimes. Perhaps the initial mass function was top-heavy, lowering true masses for the same light, because more massive stars produce more ultraviolet photons per kilogram of formed stars. Perhaps dust properties were different, shifting attenuation curves and improving fits without extreme ages, because grain composition and size distributions evolve. These are model changes that keep the clock, but alter the translation. Yet there is a harder possibility that keeps returning in the background. If redshifts are correct and luminosities remain high, then the growth mechanism must be re-examined, not merely the fitting templates. The early universe would need to assemble large stellar systems with startling speed while still obeying gravity, cooling, and feedback. That is the hinge for the next chapter's turn. We have interrogated the pipeline and watched several anomalies soften under scrutiny, and we have seen how lines, dust, lensing, and AGN can impersonate mass. Now we isolate what does not soften, and we ask what physics could accelerate early structure without breaking everything else. If the timestamp is correct, then the universe did not merely appear mature. It became mature quickly, and the mechanism matters, because mechanisms leave traces in sizes, line ratios, and star formation histories. The case files close with a question that refuses to stay local to any one galaxy, because it reaches into the rules of assembly. How could the early universe build big structures so fast and still match the other clocks? How does it reconcile luminous galaxies with the background radiation, with reionization constraints, and with the measured growth of structure later on? That question keeps LCDM on trial, without yet writing a verdict, and it keeps the central doubt alive. Webb's two early galaxies remain an invitation, not a final answer. Each spectrum narrows the range of stories we can tell, and each reanalysis tightens the priors we are willing to use. The remaining stories are fewer, sharper, and more consequential, because they survive contact with multiple lines of evidence. We move forward with the files that still resist ordinary explanations. We follow them from light to mass to time, and then to mechanism, watching each step for hidden assumptions. The mystery is no longer only what Webb saw, but what the early universe could do when the clock is unforgiving and the evidence keeps arriving. If the timestamp is correct, the problem becomes brutally practical, almost mechanical in its constraints. How do you assemble a bright galaxy in 300 million years using only known physics, with no hidden time and no new ingredients? Chapter 4 narrowed the suspects in the inference pipeline, and it did so with uncomfortable clarity. Some candidates moved closer as photometric redshift stabilized, some lost mass as templates improved, and some revealed line contamination or AGN light. A stubborn remainder still looks luminous at extreme redshift, and the clock still feels tight when we translate redshift into cosmic age. So this chapter tests the astrophysical escape routes inside LCDM. Not new cosmology yet, just faster, brighter galaxy building than we assumed, under conditions that barely resemble the modern universe. Start with the simplest lever, star formation efficiency, because it is the most direct way to buy brightness quickly. Efficiency is the fraction of a halo's baryons that become stars on short timescales, before feedback and dynamics rearrange the fuel. In the nearby universe, that fraction is modest and peaked in Milky Way, like halos, because feedback turns star formation into self-sabotage. Visually, think of a dense cloud lit from within, its edges glowing as if outlined in neon. Massive stars flood their birth clouds with ultraviolet radiation, and that radiation does more than illuminate. Radiation pressure pushes on gas and dust, and photoionization heats the surrounding hydrogen until it resists collapse, raising the effective pressure inside the cloud. Then supernovae arrive, not as a gentle fade but as a sequence of detonations. They inject energy and momentum into the interstellar medium, driving shocks that can unbind the remaining fuel, especially in shallow potential wells. The gas that might have formed the next generation is stirred, heated, and sometimes expelled into the halo. Those processes set a ceiling that is partly physical and partly statistical, because galaxies are ensembles of clouds with different densities. If too much gas turns into stars too quickly, the galaxy becomes its own wind machine, and the outflow rate can rival the inflow. The same stars that make it bright also shut the factory down, often on timescales comparable to a few dynamical times. But the early universe is not the nearby universe, and the differences are not subtle. Gas fractions are higher, densities are higher, and dynamical times are shorter inside compact halos that are still assembling. A given amount of gas can collapse faster, and inflow can replenish what feedback tries to expel, especially when the surrounding environment is itself dense. The question becomes quantitative, not rhetorical, because the baryon budget is finite. How high can efficiency plausibly climb before it violates baryon fractions, overproduces metals, or drives winds that erase the gain? And how long can an extreme phase last before the galaxy chokes on its own light, with radiation and supernovae pressurizing the very gas they need? One route is to change the fuel delivery, not the conversion recipe, because supply can compensate for waste. In LCDM, halos sit at the nodes of a cosmic web, and filaments funnel gas inward along preferred directions. At high redshift, those filaments can be dense and cold enough to stay coherent, like narrow rivers of hydrogen threading the dark. This is the cold stream picture, and it is a direct consequence of how structure grows in an expanding universe. Instead of gas shock heating to the halo's virial temperature and cooling slowly, some gas flows in along narrow channels that never fully thermalize. It radiates energy efficiently, avoids a stable accretion shock, and reaches the center quickly, delivering low-angular momentum fuel that can pile up fast. In visuals, the halo is a faint spherical glow, while the filaments are brighter strands feeding it from multiple directions. Cold streams matter because they can outrun feedback, not by resisting it, but by persisting through it. A supernova-driven outflow can clear the central region, yet the filaments keep feeding the next burst, and the duty cycle becomes a rhythm rather than a single event. The galaxy becomes less like a closed box and more like a continuously refueled engine, with inflow, star formation, and outflow running simultaneously. Rapid accretion also changes what early means, because the halo itself is not static while stars are forming. The halo can grow quickly through mergers and smooth inflow, and the gas supply can rise in step, so that yesterday's extreme becomes today's baseline. If the supply rises fast enough, high star formation rates stop being exotic and become expected, at least for the rare peaks of the density field. Yet feeding gas is not the same as turning it into starlight, and the conversion depends on how gas fragments. Fragmentation depends on cooling, and cooling depends on metallicity, which is the early universe's missing ingredient. In pristine gas, cooling channels are limited, and the limitation is microscopic as well as cosmic. Without metals and dust, gas struggles to shed energy at low temperatures, because atomic hydrogen cooling stalls once the gas becomes mostly neutral. Molecular hydrogen can help, but it is fragile under ultraviolet radiation, and its formation pathways are inefficient without dust grains. The consequence is that the gas fragments into fewer, larger clumps, and those clumps collapse into more massive stars on average. That tends to produce intense radiation fields even for modest total mass, because massive stars dominate ultraviolet output. In other words, the same gas mass can look brighter simply because it forms a different mix of stars. This leads to another escape route, a top-heavy initial mass function, and it strikes at the heart of how we infer masses. The IMF is the distribution of stellar masses at birth, and most mass in the local universe goes into low-mass stars. Low-mass stars are long-lived and dim, so they add mass without adding much light, and they quietly store baryons for billions of years. If the early IMF shifts toward higher masses, the same formed mass produces far more ultraviolet luminosity, and it does so immediately. A galaxy can look massive because it is bright, even if its true stellar mass is lower than a standard IMF would imply. The mass-to-light ratio becomes a moving target, one that can drift systematically if we assume today's IMF applies at cosmic dawn. A top-heavy IMF also changes the galaxy's timeline in a way that matters for the 300 million year constraint. Massive stars live only millions of years, so the light traces recent formation, not long-term accumulation. A galaxy can appear mature in brightness while still being young in assembled mass, like a city that looks dazzling at night, even if it was built yesterday. Yet this lever has consequences that cannot be ignored, because nature keeps accounts. Massive stars produce more ionizing photons, more supernovae, and more metals per unit formed mass, and those outputs are observable. If the IMF is top-heavy, reionization and enrichment accelerate, and other clocks must still agree with the same universe. Metallicity is not just a number in a fit, and it is not merely a label for primitive. It reshapes stellar atmospheres, stellar temperatures, and the spectrum that escapes, because metals add opacity that redistributes radiation. Low metallicity stars tend to be hotter and bluer, producing harder ultraviolet light for the same mass, and they can drive different winds that alter their lifetimes. That complicates the meaning of blue and red at high redshift, because colours are not single-cause signals. Blue can mean low dust and hot stars, but it can also mean strong line emission boosting certain bands, especially when nebular lines land inside broadband filters. Red can mean dust, or it can mean a spectral break, or it can mean an AGN continuum. Each interpretation carries a different mass. In the early universe, dust is a special case, because it plays both villain and hero. Dust reddens light and hides star formation, but it also enables cooling by providing surfaces for molecule formation, and by radiating in the infrared. Dust requires metals, and metals require earlier stars, so dust is also a record of how quickly the first generations lived and died. This brings us to population 3 and early enrichment, a concept that has been evolving for decades. The first stars form from nearly pristine hydrogen and helium, and theory predicts they skew massive because the gas cannot cool efficiently to small fragments. They burn fast, explode violently, and seed their surroundings with the first heavy elements, turning primordial chemistry into something more complex. Early enrichment can be rapid in localized regions, and locality is the key detail that smooth models often wash out. A single generation of massive stars can raise metallicity enough to change cooling and to enable more ordinary star formation afterward. The transition from pristine to enriched can happen faster than naive, volume-averaged models suggest, because metals spread unevenly through winds and turbulent mixing. Those first supernovae also create conditions for early dust production, though the efficiency is uncertain and the survival is contested. Dust can form in supernova ejecta, then be destroyed by reverse shocks, then reform in dense gas where grains can grow. The balance determines whether early galaxies redden quickly or stay blue, and it also affects how quickly molecular clouds become efficient star factories. Enrichment leaves fingerprints that Webb can test, and the tests are not just about detection, but about ratios. Metal lines in spectra, nebular line ratios, and continuum slopes all respond to metallicity and ionization, and they respond differently to stars versus AGN. If early galaxies are bright because they are metal-poor and top-heavy, their spectra should look unusually hard, with strong high ionization features and extreme equivalent widths. Another escape route is to stop assuming steady growth, because galaxies rarely behave like smooth functions. Real star formation is bursty, especially in small gas-rich systems where feedback can temporarily dominate. Feedback can drive cycles of collapse, ignition, and blowout, turning galaxies into flickering beacons that brighten and dim on timescales of tens of millions of years. Burstiness matters because surveys select on brightness, and selection is an invisible hand. A galaxy that spends most of its time faint can still dominate a catalogue if we catch it during a short peak, when its ultraviolet output spikes. The luminosity function can look inflated at the bright end, even if the time average population is less extreme, and the rare peaks are doing the statistical work. This is a selection effect with physical roots, and it is amplified by how broadband photometry works. Short bursts produce strong emission lines and high equivalent widths, which further boost broadband fluxes when those lines fall into the observed filters. The same physics that makes a burst bright also makes it easier to misread as massive, because the continuum is not the only contributor to the measured light. Burstiness also changes inferred ages in ways that can mislead even careful modelling. If the light is dominated by a recent burst, the galaxy's colours can mimic a younger or older population depending on dust and lines, and the degeneracies multiply. A single snapshot can hide a stop-and-go history that fits inside the clock, where most of the mass formed in several sharp episodes rather than one long build. Then there is the darkest escape route, early black holes, because accretion is an efficient lantern. Accretion onto a black hole converts mass to energy with high efficiency, and it can outshine stars in a compact region that is hard to resolve. In sparse data, that luminosity can masquerade as stellar mass, especially when the spectral energy distribution is sampled in only a few bands. An AGN can add a power law continuum and heat surrounding dust, reshaping infrared colours in a way that resembles a heavy stellar population. It can also drive strong lines that mimic star formation, or it can dilute stellar features that would otherwise anchor mass estimates. Even a modest AGN contribution can change the inferred stellar mass by factors, because the fit is trying to explain brightness with the wrong engine. But invoking AGN early raises its own problem, the seed black hole question, which is a race against time. To shine so brightly so early, a black hole must grow fast from an initial seed, and growth is bounded by radiation pressure. Seeds could come from the remnants of massive first stars, or from direct collapse of gas, or from dense stellar clusters where mergers build a heavier core. Each pathway has bottlenecks that are physical rather than philosophical. Stellar remnant seeds start small and must accrete near the Eddington limit for long periods, requiring sustained fuel delivery in a chaotic environment. Direct collapse seeds require special conditions that prevent fragmentation, and those conditions may be rare, because cooling and turbulence usually break gas into stars before it can collapse monolithically. Still, early black holes may be common enough to matter, even if only a fraction become luminous. If many early luminous galaxies host growing black holes, part of the too bright signal is not stellar assembly at all. It is accretion physics riding on top of young galaxies, adding light without adding the same stellar mass. These escape routes do not operate in isolation, and that coupling is where the early universe becomes most interesting. Cold streams can feed bursts, bursts can enrich gas, enrichment can change the IMF, and black holes can grow fastest in dense gas-rich centers. The early universe is a coupled system, and the fastest builders may use every channel at once, stacking advantages until the improbable becomes merely rare. So we ask what simulations say when they include these ingredients, because intuition alone cannot balance all the feedback loops. Modern hydrodynamic simulations model dark matter, gas dynamics, cooling, star formation, and feedback in expanding volumes, often with zoom-in regions for detail. They generate synthetic galaxies and synthetic surveys that can be compared to Webb, including mock photometry that passes through the same filters. Some simulations do produce rare, bright galaxies early, especially in high-density regions where the cosmic web converges. They show that extreme objects can exist without breaking LCDM, but their predicted abundance depends on uncertain subgrid physics, where unresolved processes are encoded as recipes. The uncertainty is not cosmetic, because feedback recipes control how long bursts last, how porous the interstellar medium becomes, and how much gas remains available for the next cycle. Resolution is another fault line, and it is easy to underestimate how much it matters. If a simulation cannot resolve the dense clouds where stars form, it must approximate them, and approximations can bias efficiency upward or downward. Small changes in how energy couples to gas can swing stellar masses and luminosities dramatically, because the system sits near thresholds where cooling and heating compete. Cooling and chemistry introduce further uncertainty, and they are especially treacherous at low metallicity. Metal line cooling, dust physics, and molecular hydrogen formation all affect fragmentation and star formation thresholds, and they evolve rapidly as enrichment proceeds. In the early universe, where metallicity is changing on short timescales, those details decide whether gas collapses smoothly, or in violent episodes that light up surveys. Simulations also struggle with radiative transfer at scale, because photons do not behave like passive tracers. Ionizing photons shape the interstellar medium and the escape fraction that drives reionization, carving channels and heating gas far from the stars. If the escape fraction is wrong, the inferred number of galaxies needed for reionization shifts, and the early luminosity budget is reinterpreted. The comparison to Webb is therefore a moving target, and the motion comes from both sides. Observations measure fluxes and sometimes lines, then infer masses and rates through models that assume an IMF, a dust law and a star formation history. Simulations output physical quantities, then must be converted into mock observables with the same assumptions and biases, or else the comparison is not like for like. Even so, the direction of travel is clear, and it is not a single trick. Within known physics, early galaxies can be brighter per unit mass, and they can form stars in short, intense bursts that surveys preferentially catch. They can be fed by cold streams, and they can be contaminated by AGN light, and each effect reduces the apparent tension without requiring a new universe. But the chapter's question is whether these fixes add up, not whether any one of them is imaginable. Can they explain not just a few spectacular objects, but the emerging population statistics across fields, with consistent colours and consistent line strengths? Can they do it while staying consistent with reionization timing, metal enrichment, and the later growth of structure that we see at lower redshift? There is also a quieter question hiding beneath the data, and it is worth stating plainly. If we need every lever turned to its maximum, efficiency high, IMF top heavy, bursts frequent, AGN common, does that describe a typical early galaxy, or only the rarest peaks that Webb is most likely to notice? If astrophysics can carry the load, LCDM survives with revised assumptions about early star formation, and the story becomes one of extreme environments rather than broken theory. If astrophysics cannot, the pressure shifts back to the clock itself, because the clock sets the time budget that every mechanism must obey. A galaxy cannot borrow time from feedback, and it cannot negotiate with the age of the universe. That is the transition we cannot avoid. When every local lever has been pulled, the next suspect is our cosmic ruler: distance, expansion, and the calibration of time. The next chapter follows that ruler into the foundations, where a small error can look like a universe that aged too fast, and where the simplest question becomes the hardest one. How sure are we about when early really was? We built a telescope to look back toward the beginning of time, and it returned galaxies that seemed to arrive already grown, already heavy with stars, already confident in their shapes. Chapter 4 questioned the objects, asking whether the light itself was being misread. Chapter 5 questioned the engines that build them, probing feedback, starbursts, and the speed of assembly. Now we question the ruler that turns redshift into time. Redshift is measured with impressive precision, often from a single sharp spectral feature, or a clean break in the continuum. Distance and age are inferred, and the inference depends on the universe's expansion history rather than on the galaxy alone. A galaxy's Z tells us how much space stretched during the photon's trip, not directly how many years passed. In the simplest picture, light leaves a galaxy with a well-defined wavelength, and it arrives stretched by the factor we call 1 plus Z. That stretch is geometric, a record of the scale factor changing while the photon crossed expanding space. Yet the same stretch can correspond to different travel times if the expansion rate was faster or slower along the way. The ruler is not a stick, it is a history. To translate Z into million years after the Big Bang, we integrate an expansion rate across cosmic time, accumulating small changes into a final age. That rate is set by parameters like H0, matter density, radiation, and dark energy's behaviour, each shaping a different era. Change those numbers slightly, and the same redshift maps to a different age, sometimes by tens of millions of years where Webb is most sensitive. The mathematics behind the narration is quiet but decisive. The Hubble parameter, Hz, is the clock's ticking rate, and the age comes from integrating 1 over it. Matter makes Hz larger at high redshift because density rises as the universe shrinks. Dark energy dominates later, altering the recent part of the integral that anchors the whole timeline. Even radiation, usually ignored at low redshift, matters near the earliest chapters where seconds become structure. This is why the early galaxy debate cannot stay local to any one spectrum or any single mass estimate. If the timeline is off, every claim about too early shifts with it, like moving the tick marks on a ruler. The central question becomes whether Webb is seeing impossible growth or a miscalibrated clock. In LCDM, the conversion is usually anchored by a best-fit model to many datasets, each acting like a different witness to the same event. The cosmic microwave background fixes a geometry and a scale at recombination when electrons and protons first combined into neutral atoms. Supernovae and galaxy clustering constrain how expansion changed later, when dark energy began to matter. The result is a tight redshift to distance relation, and from that, a tight redshift to age relation. Visually, this tightness looks like a smooth curve drawn through the universe, a single mapping from Z to cosmic time that feels almost mechanical. In animations, the curve barely wiggles as new measurements arrive, which tempts us to treat it as settled. But tight is not the same as unbreakable, and precision is not the same as certainty. The mapping relies on assumptions about what the universe contains and how those contents evolve. If any component behaves differently, the ruler bends without snapping, and the bend can hide in places we do not look first. A small change in early expansion can shift a standard scale, which then shifts inferred distances everywhere. A small change in late expansion can tilt the recent part of the timeline, which then changes how we interpret ancient light. The danger is subtle. The model can remain internally consistent while still being wrong. The most famous crack is the Hubble tension, a disagreement that has survived years of scrutiny and improved calibration. One set of methods measures H0 from the nearby universe using distance ladders, built step by step from geometric anchors. Another infers H0 from the early universe using the CMB within LCDM, extracting a present-day number from ancient patterns. They disagree beyond expected errors, and the gap has become a pressure point in modern cosmology. The distance ladder starts with geometric anchors, where distances are measured without assuming a cosmological model, using parallax and other direct methods. Those anchors calibrate standard candles, objects whose intrinsic brightness can be inferred from observable properties. Cepheids set distances to supernova-host galaxies because their pulsation periods correlate with luminosity in a well-tested relation. Type Ia supernovae extend the ladder deep into the Hubble flow, where peculiar velocities fade and expansion dominates. That chain tends to prefer a higher H0, meaning a faster expansion rate today, and it does so with a logic that feels almost tactile. You can picture it as a series of overlapping circles of certainty, each one stepping outward into deeper space. But each step also inherits systematics from the step below, and the ladder's strength depends on how well those inheritances are controlled. Dust, metallicity, crowding, and calibration drift are not dramatic villains, yet they can bias a number by a few percent. The CMB method is different in spirit, and it feels more like forensic reconstruction than direct measurement. It measures angular patterns in a 13.8 billion-year-old snapshot, then fits a model that predicts today's expansion rate from early conditions. The acoustic peaks are not random bumps. They are the frozen imprint of sound waves in the primordial plasma. Their spacing and heights encode the composition of the universe, the baryon fraction, and the scale of a standard ruler set before atoms formed. That inference tends to prefer a lower H0, and it does so with remarkable internal coherence across multiple CMB datasets. The disagreement is not about one instrument, but about two eras that should connect smoothly if the model is complete. It is as if two clocks, both carefully built, disagree about the same elapsed time. The question becomes uncomfortable. Which clock is misreading, or what physics is missing between them? A higher H0 means the universe expands faster today, and that usually implies a younger universe for the same matter content and the same early conditions. A lower H0 implies an older universe and more time for early growth, which can ease the pressure on Webb's earliest galaxies. Either direction changes how tight Webb's early timeline feels, because at redshifts above 10 the age of the universe is measured in hundreds of millions of years. When the entire epoch is short, a small percentage shift becomes a large fraction of the available time. Yet the tension is not solved by simply choosing a side, because the universe must agree with itself across redshift. If we raise H0 in the model, we must still match the CMB peak structure and the observed clustering at intermediate times. If we lower H0, we must still match the supernova Hubble diagram and local calibrations with their own consistency checks. The ruler must stay consistent across the whole cosmic record, from recombination to the present sky. This is where early universe modifications enter, because they can change inferred distances without rewriting late-time physics in an obvious way. The key idea is the sound horizon, a physical scale set by how far pressure waves could travel in the early plasma before recombination. In that hot mixture of photons, electrons and baryons, gravity tried to compress matter while radiation pressure pushed back. The tug-of-war launched oscillations, and those oscillations left a standard scale imprinted in the CMB and in baryon acoustic oscillations. If the sound horizon was smaller than LCDM predicts, the same observed angles in the CMB would imply different distances to the last scattering surface. That can push the inferred H0 upward while keeping the CMB fit acceptable, because the model can trade one scale for another. It is a way to reconcile early and late measurements by changing the early ruler rather than the late expansion. In other words, you keep the map, but you redraw the scale bar. Early dark energy is a leading example, and its appeal is its restraint. It proposes a brief extra energy component active before recombination, then fading away so that the later universe behaves almost normally. That extra energy speeds up early expansion, reducing the time available for sound waves to travel, and therefore shrinking the sound horizon. The late universe can still look like LCDM afterward, which is why the idea remains on the table. In this picture, the Big Bang is not discarded, and the familiar milestones still occur in the right order. The hot early phase remains and recombination still happens, releasing the CMB photons that now bathe the universe. What changes is the detailed expansion rate during a narrow window, a subtle reshaping of the timeline's curvature. A small early change can echo into big shifts in inferred parameters, because the CMB is a high-leverage data set. But early dark energy is not a free pass, and the CMB is not easily fooled. It must fit the CMB power spectrum, including peak heights, relative spacing, and the damping tail where photon diffusion smooths small-scale fluctuations. It must not spoil nucleosynthesis yields, because the early expansion rate affects how protons and neutrons froze into light elements. It must not overproduce structure, because changing early dynamics can change the growth of perturbations. It must also remain compatible with lensing of the CMB and with large-scale clustering measured at later times. Other extensions aim at the same lever, and their differences are often technical rather than theatrical. Some change how dark matter behaves at early times, altering growth and the CMB fit while leaving late-time gravity mostly intact. Some introduce interactions in the dark sector that shift perturbations, changing how density waves propagate and freeze. The goal is consistent: adjust early physics to reconcile the ruler's calibrations without breaking the rest of the cosmic ledger. Curvature is another subtle bend, and it has a long history in cosmological argument. LCDM usually assumes spatial flatness, supported by CMB data and by inflationary expectations that drive curvature towards zero. But small curvature can change distance redshift relations, especially at high redshift where geometry accumulates along long lines of sight. Even tiny deviations can shift inferred distances and ages, and those shifts can masquerade as changes in other parameters. Curvature also couples to other parameters through degeneracies, which are the model's own blind spots. A slightly curved universe can mimic changes in dark energy or matter density in some datasets, because multiple combinations can produce similar angular scales. That means a fit can hide curvature inside other numbers, unless multiple probes break the degeneracy. The universe can look flat from one angle while quietly curving in another, at least until the data become decisive. Neutrinos add another quiet uncertainty, because they are both abundant and elusive. In the early universe, relativistic species contribute to radiation density, and radiation density affects expansion before recombination. That early expansion changes the sound horizon, which then changes the inferred distance scale. The parameter Nef captures any extra relativistic energy beyond standard neutrinos, including the possibility of additional light species. If Nef is higher, early expansion is faster, and the sound horizon shrinks, which can move inferred H0 upward in a way similar to early dark energy. But Nef is constrained by the CMB and by primordial element abundances, which act like a chemical audit of the first minutes. The ruler can bend, but only within tight bounds, and those bounds tighten as measurements improve. Neutrinos in effect offer flexibility but not freedom. These parameter shifts also affect structure growth, and that is where Webb's galaxies re-enter the story with force. Faster early expansion can suppress growth by reducing the time gravity has to amplify perturbations, even while it changes the inferred ages. Changes in neutrinos can damp small-scale power through free streaming, because fast particles smear out density contrasts. Any fix for H0 must still produce the right abundance of galaxies later, not just the right numbers on a plot. That matters for Webb's puzzle, because early galaxies are not only timestamps, they are also growth markers, testing how quickly halos and stars assembled from the initial fluctuations. If we change the expansion history, we change both the time available and the predicted growth rate, and those changes can pull in opposite directions. More time does not automatically mean easier formation if the growth of structure is simultaneously slowed. Even if the ruler is correct, another layer complicates what we think we see, and it lies between us and the galaxies. The intergalactic medium is not a transparent window at all times, especially in the ultraviolet where hydrogen is hungry for photons. Before ionization completes, neutral hydrogen absorbs ultraviolet light efficiently, carving deep troughs into spectra. Afterward, residual opacity still shapes what escapes, and it can make the universe look emptier than it truly is. Ionization is therefore part of the measurement framework, not just a chapter of astrophysical history. It affects the Lyman break used for photometric redshifts, because the break's sharpness depends on how much absorption occurs along the line of sight. It affects the visibility of Lyman alpha in spectra, because that line is easily scattered by neutral hydrogen. It also affects how we interpret first light, because visibility depends on the medium's state as much as on the galaxy's power. This is the key distinction, and it is easy to forget when looking at a bright point on a deep image. Visibility is not the same as existence, and the universe has many ways to hide what it contains. A galaxy can form stars while its most diagnostic photons are absorbed or scattered, leaving only a muted continuum behind. Our catalogues are shaped by what escapes, not by everything that happens, and that selection is physical as well as instrumental. Opacity can also bias inferred ages and star formation histories, because the templates we fit are only as good as the assumptions inside them. If the IGM suppresses flux in certain bands, templates may prefer different redshifts or dust levels to explain the missing light. That can move objects along the distance ladder inside the photometric pipeline, shifting Z estimates in coherent ways. The ruler is not only cosmology but also transmission through a changing medium. Then there is the problem of selection, which is less glamorous than new physics but just as consequential. Webb's first deep fields were small in area, chosen for practical reasons and low foreground contamination, and they were designed to maximize early returns. Small areas sample a limited cosmic volume at each redshift slice, like drilling a narrow core through a mountain and guessing the whole geology. Limited volume increases the role of cosmic variance, and cosmic variance is the universe's refusal to be uniform on small patches. Cosmic variance means the universe is lumpy, and a small patch can be atypical without being misleading on purpose. A field can land on an overdense region where galaxies form earlier and brighter, because the underlying dark matter is already concentrated. Another field can land on a void and look empty at the same depth, even if the global average is healthy. Early results can therefore overstate typical abundance, especially when the most dramatic objects attract the most attention. Selection effects also come from detection thresholds, because surveys find what rises above noise, and bursty galaxies rise above noise more often. A galaxy that forms stars in pulses can briefly become visible at extreme redshift, then fade below detectability, biasing samples toward rare bright phases. Lensing can magnify sources into the sample, and even modest magnification can move an object across a catalogue cut. Photometric priors can favour high Z solutions when templates are incomplete, and the catalogue is not a random draw. This is why population claims matter more than single headlines, and why the field has been cautious even when the images are astonishing. One extreme galaxy can be a statistical fluke, a lensing boost, or a modelling artifact that evaporates under reanalysis. A true challenge to LCDM would be an excess that persists across many independent fields, with different sightlines and different foregrounds. It would survive different pipelines and different teams, and it would remain after the easy biases are removed. Breaking LCDM would also require robust spectroscopy, because photometric redshifts can be wrong in coherent ways. At high redshift, emission lines can masquerade as continuum breaks, and dust can redden a spectrum until it imitates distance. Spectra must confirm redshifts and constrain line contamination, ideally with multiple features that agree. The mass and age inferences must be stress-tested with multiple models, because stellar population synthesis has its own uncertainties at low metallicity in young ages. The standard for break is therefore high, and it is intentionally high because the claim is so large. We would need a measured luminosity function and stellar mass function at high redshift that exceed LCDM predictions by large factors, not by marginal shifts. We would need that excess after correcting for completeness, lensing, and cosmic variance, with error budgets that do not quietly assume the answer. We would need agreement with reionization constraints and with CMB calibrated parameters, so that one fix does not create 3 new problems. So far, the story is not a verdict, and the uncertainty is part of the drama rather than a failure of method. It is a narrowing corridor of possibilities, where each new dataset closes one door and leaves another barely open. Some anomalies soften when the pipeline improves, and some shrink when spectroscopy replaces photometry. Some remain as tension points that motivate new parameters rather than new origins, which is how science often advances. Still, the ruler question changes the mood of the mystery, because it shifts the debate from objects to foundations. If we can shift the expansion history even slightly, the early universe gains or loses precious time, and those millions of years matter. If we cannot, then the remaining 2 early cases become more consequential, because they cannot be dismissed as bookkeeping. They would demand either extreme astrophysics, unusually efficient star formation, rapid metal enrichment, aggressive merging, or deeper revisions. The deeper lesson is that cosmology is an inference network, and networks can transmit small errors into large conclusions. Redshift connects to distance through a model, and that model is constrained but not omniscient. Distance connects to luminosity and mass through astrophysics, which depends on dust, metallicity, and stellar evolution. Mass connects to growth through gravity and feedback is a complicated conversation between radiation, gas, and black holes. A small bend in one link can look like a crack in the whole chain, especially when the data are new and the stakes are high. When we say, this galaxy is too massive at this time, we are stacking assumptions like transparent sheets. The picture is sharp only if the sheets are aligned, and misalignment can mimic discovery. The unsettling question is not whether errors exist, but whether they align in a direction that matters. We are left with a careful tension, and it is the kind that drives long nights of analysis. The Big Bang framework can absorb some strain through parameter shifts and early universe tweaks, and it has done so before in the history of cosmology. But those tweaks are constrained by a web of independent measurements, from the CMB to element abundances to clustering statistics. The ruler can warp, yet it cannot fold in half, and the allowed warping is becoming better measured. And that brings us to the next threshold, where the mystery becomes less about calibration and more about origin. If the ruler is already near its allowed limits, and if the galaxies still look too mature, then the discomfort moves upstream. We begin to consider models where the Big Bang is not page 1, but a later chapter in a longer story. We built a telescope to look back toward the beginning of time, and it forced us to ask whether our definition of beginning was always an interpretation. The next chapter follows that suspicion into scenarios that keep the data, but rewrite the origin. We built a telescope to look back toward the beginning of time, and it returned galaxies that seemed to arrive already experienced, already structured, already busy with stars and heavy elements. In the deep fields, the screen fills with pinpricks and smudges, and each smudge is a system with a history. If the ruler is close to its limits, the next question is upstream. Was the Big Bang the absolute beginning, or only the last reset we can still see? Before speculation hardens into myth, we have to define the boundary with care. In modern cosmology, the Big Bang means an early hot dense phase with rapid expansion and cooling, a phase we infer from multiple lines of evidence. It does not automatically mean a literal explosion into empty space, because space itself is what expands. It does not automatically mean a singular first moment where physics stops, because our equations may be the part that stops. Historically, the phrase Big Bang was coined as a jab, not a hymn, and the name stuck because it is vivid. The evidence that followed was less theatrical and more forensic. Hubble's expansion, primordial element abundances, and then the cosmic microwave background. When we say beginning, we often mean the earliest time our tested model describes, which is a more cautious claim. That caution matters because the universe can be older than our math. The standard model still has a hard edge, even when we phrase it carefully and avoid metaphysical language. Extrapolate the equations backward, and densities rise, temperatures rise, and the math points toward a singularity where curvature becomes infinite. Many physicists treat that singularity as a sign of missing physics, not as a proven event in nature. The question becomes whether new physics merely smooths the edge, or replaces the beginning with a prior chapter. Any alternative has to do two jobs at once, and neither job is negotiable. It must remove or reinterpret the singularity, and it must reproduce the successful ledger of LCDM across many datasets. It must still yield the light element abundances from primordial nuclear synthesis, which are sensitive to the early expansion rate. It must still generate the CMB's acoustic peaks and polarization patterns, which encode a precise early universe sound horizon. It must still grow the cosmic web into the galaxy clustering we map today, including the lensing signatures that trace mass we cannot see. Start with the simplest rewrite that keeps the hot early phase, because that hot phase is not optional. A bounce replaces the singularity with a transition from contraction to expansion, like a cosmic spring that compresses and releases. The universe shrinks, heats, and reaches a minimum size, then re-expands into the familiar cooling history. The hot dense state remains, but it is no longer the first page. A bounce is not a single model, but a family with different engines and different failure modes. Some use quantum gravity effects that create repulsive pressure at extreme density, where spacetime itself becomes granular. Some use exotic matter components with negative pressure that violate classical energy conditions, rules that normally keep gravity attractive. Some use modified gravity, where Einstein's equations change at high curvature and prevent infinite compression. The technical promise is clear, and the technical burden is heavy, because contraction is a dangerous place for a universe. A successful bounce must be stable, not a fine-tuned trick that collapses into chaos after a tiny perturbation. It must avoid runaway anisotropy, where small directional differences dominate during contraction and shred smoothness. It must avoid the BKL instability, where contraction amplifies shear and curvature into a messy, inhomogeneous end. Then comes the observational accounting, because the CMB is not forgiving and it remembers details. In inflationary LCDM, quantum fluctuations are stretched and become nearly scale invariant, with a slight tilt that matches the data. Those fluctuations seed the acoustic pattern we measure in the CMB temperature spectrum, a set of peaks that behave like a calibrated instrument. A bounce must generate comparable primordial perturbations with the right tilt, amplitude, and phase, not just something roughly similar. Some bouncing scenarios try to replace inflation rather than keep it, and that is where the models become sharply distinct. In ekpyrotic models, a slow contraction with a very stiff equation of states smooths and flattens the universe, acting like a cosmic ironing board. That contraction can suppress anisotropies and generate perturbations through additional fields that carry fluctuations safely through the bounce. The bounce then converts those perturbations into the expanding universe's initial conditions, and the conversion has to be precise. Other bounce models keep a short inflationary phase after the bounce, which is a pragmatic compromise rather than a pure alternative. That move can rescue the perturbation spectrum and dilute unwanted relics, including curvature and exotic particles. But it also blurs the philosophical payoff, because inflation already pushes the beginning into an earlier unknown. The question shifts from before the bang to what set the bounce and the inflation, and whether those settings leave a trace. A bounce also changes the meaning of ancient light in a subtle way, and the subtlety is where tests live. The CMB still forms at recombination, long after the bounce, so it does not directly show the pre-bounce era. But pre-bounce physics can leak into the larger scales, where modes were outside the horizon longest and had the most time to carry memory. That is where anomalies and correlations become tempting clues, even if they are statistically fragile. Cyclic universes push the idea further, turning one bounce into a repeating rhythm with a kind of cosmic heartbeat. Expansion slows, reverses, contracts and bounces again, potentially forever, with each era leaving behind a faint imprint. The appeal is narrative as much as mathematical, because it replaces a single origin with an eternal process. The universe becomes a sequence of eras rather than a one-time event, and the camera can linger on that repeating arc. Cyclic models face a problem that is not optional, because thermodynamics is not impressed by elegance. Entropy tends to increase, and in a naive cycle it accumulates from one round to the next like ash that never blows away. That would make each cycle larger, longer, and more dilute, and it would still point backward to a beginning. Any serious cyclic model must explain how entropy is diluted, exported, or effectively reset, without simply declaring it so. Different proposals attack the entropy problem in different ways, and each solution has a cost. Some use a phase of accelerated expansion that stretches space and dilutes entropy density, making the next cycle begin in a cleaner patch. Some invoke brane collisions or extra-dimensional dynamics that change what volume means across cycles, so entropy bookkeeping is not straightforward. Some propose that black holes and other high-entropy structures are removed from the observable patch before the next contraction, leaving behind a lower entropy region that can cycle again. The observational demand remains the same, even if the metaphysics changes and the timeline loops. A cyclic model must still reproduce the CMB peak structure, which encodes a precise early universe sound horizon and a precise baryon loading. It must still reproduce baryon acoustic oscillations in galaxy clustering at later times, which act like a standard ruler in the cosmic web. It must still match the success of BBN, which depends on the expansion rate during the first minutes and the number of relativistic species. Cyclic models also make specific kinds of predictions, even when they try to hide their tracks. Repeated cycles can imprint subtle departures from Gaussian statistics in primordial fluctuations, because the mechanism is rarely as simple as single-field slow roll. They can generate distinctive running of the spectral index across scales, changing how power shifts from large to small angles. They can also leave residual correlations on the largest angular scales, where the CMB already looks slightly strange and slightly unfinished. Now shift to a different kind of before, one that avoids dramatic contraction and instead stretches time. Emergent universe scenarios propose a long, quasi-static or slowly evolving phase before expansion begins, like a universe that lingers on a plateau. The universe exists for a very long time in a near-equilibrium state, then transitions into the hot expanding phase through an instability. The Big Bang becomes a phase change rather than a creation event, and the visual becomes less explosion and more ignition. Emergent models try to solve a different discomfort that Webb has made emotionally vivid. If the early universe is extremely young, then Webb's mature galaxies feel like a race against a tight clock, with little time for assembly and enrichment. If there is a long prelude, some early structures might be reinterpreted as products of a longer preparation, not a miraculous sprint. The challenge is making that prelude stable without fine-tuning, because a static universe is usually precarious. A quasi-static phase must resist collapse and resist runaway expansion, which is a delicate balancing act in general relativity. It must also generate the right perturbations, because structure still needs seeds, and those seeds must have the observed statistics. Some models use scalar fields trapped in metastable states, then released as the field rolls and reheats the universe. Some use modified gravity that allows static solutions that later destabilize into expansion, turning stability into a timed trigger. Pre-Big Bang scenarios from string-inspired ideas offer another route, and they come with their own vocabulary and their own hopes. They imagine a dilaton-driven phase where the universe evolves from a cold, empty state into a hot, dense one, with the coupling strengths changing in time. The transition can resemble a bounce, but the underlying degrees of freedom differ from standard fields, and the symmetry structure is richer. The observational question becomes whether any distinctive relic survives into the CMB and large-scale structure, rather than being erased by later dynamics. At this point, the story risks becoming a catalogue, so the discipline must be explicit and repeated as a rule. These are not free inventions that can fit anything, because the universe has already left us a detailed receipt. Each model must pass the same gauntlet of constraints that built confidence in LCDM, and the gauntlet is designed to expose hidden costs. If a model gains a beginning but loses the peaks, it is not a gain. Begin with BBN because it is a chemical audit of the first minutes, written into the oldest matter we can sample. The helium fraction, Deuterium abundance and lithium problem constrain the expansion rate and particle content, including any extra radiation-like energy. Change early expansion too much, and the neutron-to-proton ratio freezes differently, shifting reaction pathways in measurable ways. That shifts element yields in ways we can measure in ancient gas and stars, and the margins are not generous. Then the CMB, because it is a precision spectrum, not a vague glow, and it carries multiple layers of information. The acoustic peak positions fix geometry and the sound horizon, effectively measuring how far sound waves travelled before recombination. The relative peak heights fix baryon density and matter density, because baryons load the oscillations like weight on a spring. The damping tail fixes diffusion physics and the thickness of last scattering, where photons random walk out of the plasma. Polarization adds another layer, including E modes and lensing-induced B modes that trace structure between us and the surface of last scattering. Large-scale structure adds a third accounting system, and it tests time evolution rather than a single snapshot. Galaxy clustering, weak lensing, and cluster counts track how perturbations grew over time, and they respond to both gravity and the contents of the universe. Any modified early history must still land on the observed matter-power spectrum, including its shape and amplitude. It must still match the growth rate inferred from redshift space distortions, where peculiar velocities reveal gravitational pull. It must still respect the lensing of the CMB, which integrates structure along the line of sight and is difficult to evade. If Webb's galaxies are truly too mature, one could also change growth without changing the background expansion much, which is a subtler intervention. That is where modified gravity and dark sector complexity enter as serious testable ideas rather than narrative escapes. Instead of adding time, you change how efficiently gravity builds structure, especially at high redshift where small differences compound. You can accelerate early collapse while keeping distances nearly standard, but you must not break the late-time universe. Modified gravity comes in controlled frameworks, not just hand-waving, and many were developed long before Webb. Scalar tensor theories add a field that changes the effective strength of gravity in time or environment, often through a coupling that can evolve. FR, gravity alters the relationship between curvature and stress energy, typically introducing an extra scalar degree of freedom in disguise. Massive gravity and other constructions change how gravitational degrees of freedom propagate, and that can affect growth and lensing in linked ways. But modified gravity is constrained by more than cosmology, which is why many attractive ideas are also cornered. Solar system tests, binary pulsars, and gravitational wave propagation limit how much gravity can differ from general relativity, especially in how waves travel and decay. Many models rely on screening, which must work across scales and epochs, hiding deviations in dense environments while allowing them in cosmic voids. The cosmological freedom is real, but it is not unlimited, and the allowed space is narrow. Dark sector complexity offers another lever that stays within general relativity, which can be appealing if you want to keep spacetime itself conventional. Dark matter might not be perfectly cold and collisionless, as the simplest simulations assume, and small interactions can matter early. It might have self-interactions that change halo structure and merger rates, altering how quickly dense cores form. It might interact weakly with dark radiation or dark energy, altering perturbation growth while leaving the background expansion close to LCDM. Warm dark matter suppresses small-scale structure, which usually delays early galaxy formation rather than speeding it up, so it is not an obvious fix. But some interacting models can change collapse thresholds and baryon accretion histories in non-intuitive ways, especially when feedback and cooling are included. The point is not that any one variant solves Webb's puzzle, because the puzzle itself is still being measured. The point is that the dark sector is inferred, and inference leaves room for richer behaviour. These ideas also connect back to the Hubble tension logic from the previous chapter, where early time tweaks can echo into late time inferences. Early universe changes that shrink the sound horizon can shift inferred parameters, including H0, without changing the observed angular peak positions. But those same changes can alter structure growth and lensing in ways that are already tightly measured, especially by CMB lensing and galaxy surveys. A model that fixes one tension can worsen another, and the data demand a global fit rather than a local patch. So what would count as a distinguishing signature? Beyond philosophical satisfaction, and beyond a clever story. The cleanest targets are primordial gravitational waves and primordial non-Gaussianity, because they reach back toward the mechanism itself. Inflation predicts a spectrum of tensor modes tied to its energy scale, though the amplitude may be tiny and still below current limits. Some bounce and cyclic models predict different tensor tilts, different amplitudes, or sharp features that behave like a scar. CMB mode polarization is the classic hunting ground, but it is not the only one, and the search is becoming multi-band. A stochastic gravitational wave background could also be probed by pulsar timing arrays at nanohertz frequencies, where supermassive black hole binaries are a foreground. Space-based interferometers could probe millihertz bands where phase transitions and cosmic strings might contribute, depending on the model's details. The frequency dependence becomes a fingerprint of the early mechanism, because different origins populate different parts of the spectrum. Non-Gaussianity is another discriminator because it is hard to fake, and it is hard to erase without leaving other traces. Single-field slow-roll inflation predicts nearly Gaussian fluctuations with small specific deviations, constrained by consistency relations. Alternatives can produce larger local-type non-Gaussianity, or characteristic shapes in the bispectrum that encode multi-field dynamics or non-standard initial states. Large-scale structure surveys can constrain these shapes through scale-dependent bias and higher-order correlations, turning galaxy maps into statistical microscopes. Large-angle CMB anomalies remain a provocative but fragile clue, like a whisper at the edge of hearing. There are hints of low quadrupole power, alignments, and hemispherical asymmetry, and some maps look slightly too patterned. Some pre-Big Bang scenarios could produce suppressed power on the largest scales, or unusual correlations that survive because those modes were never fully randomized. But cosmic variance is severe at large angles, so the evidential bar is high, and caution is part of the method. Ryanization history is a quieter but powerful test, and it loops Webb back into the origin story through astrophysics rather than metaphysics. If galaxies formed earlier or more efficiently, the ionizing photon budget changes, and the intergalactic medium responds like a fog lifting. The CMB optical depth constrains the integrated electron column, limiting how early rionization can begin without overshooting the measured scattering signal. Quasar absorption spectra constrain how late neutral hydrogen persists, showing us when the last islands of neutrality disappeared. An altered early universe could also change the timing and patchiness of reionization, and patchiness matters because it affects what we infer from light. That would affect the visibility of Lyman alpha and the interpretation of dropout selections, where dust and gas can masquerade as distance. It would also affect 21 centimeter signals from neutral hydrogen, which can map heating and ionization across cosmic dawn with spatial detail. The 21 centimeter sky becomes a direct probe of the era Webb samples indirectly, and it can test whether too early is real. Now the philosophical implication returns, because it is part of why these models attract attention, even among careful scientists. If the Big Bang is a phase, then beginning becomes a boundary of our current physics, not necessarily of reality, and that boundary can move. If the universe cycles, then time may extend indefinitely, but explanation shifts to the rule that enforces the cycles and keeps them stable. If the universe emerges from a static past, then the question becomes why it waited, and what finally tipped it into change. Yet discipline matters more here than anywhere in the film, because the temptation to overread is strongest at the edge. Webb's early galaxies are a tension, not a proof of prehistory, and tensions often dissolve under better calibration. A single surprising dataset can be a systematic error, a selection bias, or an astrophysical extreme that our simulations undersampled. Extraordinary claims require converging confirmation from independent probes that do not share the same assumptions, and that convergence takes time. So the standard of evidence must be stated as part of the story, not as a footnote. A viable alternative must match the CMB with the same precision as LCDM, including polarization and lensing. It must match BBN abundances within measured uncertainties, without introducing new conflicts in deuterium or helium. It must match lensing and clustering across redshift, not just at one convenient epoch. It must also explain why it does not contradict local gravity tests and gravitational wave observations, which are now part of Cosmology's constraint network. This is why the climax feels like standing at a threshold rather than crossing it, with the door still closed but the hinges visible. The alternatives are radical in implication, but serious in their mathematics and in their willingness to be tested. They do not ask for belief, and they do not ask for loyalty to a camp. They ask for measurements that can discriminate, and for models that survive contact with those measurements. Return to the central question, now sharpened into something operational. Are Webb's mature early galaxies exposing a flaw in our measurements and models of the young universe? Perhaps in dust, lensing, or star formation efficiency? Or are they hinting that the hot dense phase was not the first chapter, and that our timeline has a missing page? The difference is not a mood, it is a program of tests, and the program has milestones. The next step is to turn speculation into a measurable frontier. Webb can expand survey area to beat down cosmic variance and build robust luminosity functions, so rare objects stop dominating the story. Webb spectroscopy can confirm redshifts, measure metallicities, and separate stars from accreting black holes, which can mimic stellar light. Strong lensing fields can push to fainter galaxies that dominate rionization, tightening the photon budget and clarifying whether early light is common or exceptional. Upcoming observatories widen the net and reduce single-instrument risk, which is how science turns surprises into conclusions. Roman will map wide infrared fields and find rare, bright objects with better statistics, testing whether Webb's early sample is unusual. Euclid will add clustering and lensing over huge volumes, constraining growth and non-Gaussianity with sheer scale. Ground-based CMB experiments will refine polarization and lensing, hunting for tensors and tightening early universe parameters that alternatives must respect. And if the early universe left a different kind of relic, new instruments will listen with different senses. 21-centimeter experiments aim to map neutral hydrogen through cosmic dawn, turning the dark ages into an observable landscape. Pulsar timing arrays and future interferometers will search for gravitational wave backgrounds with distinctive spectra, separating astrophysical hum from primordial signal. Multiprobe cosmology becomes the method, because no single observation can carry a claim this large. So we end this chapter where the mystery becomes sharpest. With the data still arriving and the theory still flexible, the Big Bang may be more resilient than its critics claim, absorbing Webb's surprises through better astrophysics and better calibration. Or it may be more mysterious than its defenders imagined, with a prelude written into subtle correlations and ancient light. Either way, the next chapter is not about belief. It is about what we can test next, and how soon the universe will answer. Now mystery becomes method, and Webb's next steps are statistical and surgical. Wider surveys reduce cosmic variance, so a single lucky deep field cannot masquerade as a universal truth. Lensing fields extend counts into the faint majority, where magnification by foreground clusters turns invisible galaxies into measurable smudges. Deeper spectroscopy confirms redshifts, separates breaks from emission lines, and tightens modelling pipelines that translate photons into ages and masses. It is slow work. Calibration files, selection functions, and simulations that reveal what the telescope might be missing. Triangulation follows. ALMA measures dust and gas, showing whether early starlight is being hidden and reprocessed into millimeter glow. Hubble archives test evolution, letting us compare morphologies across time with the same careful biases. Extremely large telescopes add decisive spectra, resolving line ratios that can expose hot stars, shocks, or accreting black holes. Roman will map wide infrared fields, building lensing and clustering statistics at scale, and turning rare discoveries into populations. The debate turns on measurements. Stellar masses, star formation rates, AGN fractions, halo masses from lensing, and the Z10 luminosity function must all converge. Rionization crosschecks must agree, using quasar-damping wings, 21-centimeter experiments, and CMB polarization that remembers when the fog lifted. Challenging the Big Bang likely means refined physics, not erasure, though new ingredients remain possible. Webb has not overthrown the Big Bang, but it has exposed our assumptions. Ancient light is a test, and the next photons may decide whether the beginning was a moment or a memory. Webb's deep fields began as a near-black postcard from the early universe, crowded with red smudges that looked too bright, too compact, and too mature. As we followed those photons through mirrors, detectors, and templates, the mystery shifted from what we saw to how we know, exposing how dust, emission lines, lensing, AGN light, and SED assumptions can reshape a galaxy's supposed age and mass. Then we widened the frame to the model itself, LCDM's clock and ruler, where the CMB, reionization, and the halo mass functions set hard expectations. Yet the Hubble tension hints our calibration may still be incomplete. Even after the pipeline triage, a stubborn subset remains luminous at a few 100 million years, forcing us to test whether early galaxies simply grew faster, with denser gas, burstier star formation, and different first stars than we expected. And if those astrophysical levers cannot carry the weight, the pressure moves deeper toward the expansion history that turns redshift into time, and toward the unsettling possibility that the beginning is a boundary of our description, not of reality. Finally, we looked ahead to the next clues, where wider surveys, lensing fields, and decisive spectroscopy will turn anecdotes into statistics, and multi-observatory triangulation will audit every assumption. In that coming cross-check, ALMA's dust and gas, Roman's wide maps, ELT line ratios, 21 centimeter shadows, and CMB polarization, the universe will either harmonize our story or demand a new verse. What then is broken? Our measurements, our models, or the story itself? And is Webb hinting the Big Bang wasn't the absolute beginning? The honest answer is that Webb has not delivered a verdict. It has delivered an invitation. Interrogate every link in the chain, because the chain is the claim. If the redshifts fall, the impossibly old cities dissolve into nearer lights, and the Big Bang stands taller for surviving a sharper test. If the redshifts hold, and the masses and number counts remain after dust, lines, lensing, and AGN are accounted for, then either galaxies learn to build faster than our simulations allow, or our cosmic clock is subtly misread. And if the clock itself must change, the question of before returns, not as a loophole, but as a disciplined demand that any deeper origin match the full evidence ledger. In the end, those tiny red smudges are not just distant objects, they are arguments made of light, each photon a timestamp, each spectrum a witness, each uncertainty a doorway. The Big Bang may prove more resilient than its critics claim, or more mysterious than its defenders imagined, but either way the night sky is telling us the same thing. Beginnings are not found by insisting, they are found by measuring. So keep watching the data as it arrives, and ask the hardest question with every new image. What assumption did we just test, and what did the universe say back? What then is broken? Our measurements, our models, or the story itself? And is Webb hinting the Big Bang wasn't the absolute beginning? The honest answer is that Webb has not delivered a verdict, it has delivered an invitation. Interrogate every link in the chain, because the chain is the claim. In the end, those tiny red smudges are not just distant objects, they are arguments made of a light, each photon a timestamp, each spectrum a witness, each uncertainty a doorway. The Big Bang may prove more resilient than its critics claim, or more mysterious than its defenders imagined. But either way, the night sky is telling us the same thing. Beginnings are not found by insisting, they are found by measuring. So keep watching the data as it arrives, and ask the hardest question with every new image. What assumption did we just test, and what did the universe say back?